2, class 12 track 1, class 12 track 2. This is the part from where most of the question come. So without wasting time, we are going to cover everything from this part. So first of all, I am going to talk about every single heading one by one by one by one, and whatever question can come from that, we will try to cover in this series. So let's not waste time. First of all, let's start electric charge and field. First is introduction, electric charge, and then there are properties of electric charge. So there are conductors and insulators. Conductors are the one which have free electrons, and insulators do not have free electrons. Then basic property of electric charge. First, charge is additive. Charge is a scalar quantity and it can be added. So if a body already has charge of 2 coulomb and you give it one more charge of 1 coulomb, then the total charge becomes 3 coulomb. Charge is additive. Next property, charge is conserved. Principle of conservation of charge is one of the most basic fundamental principle of conservation. There are 4 principles of conservation in our course. Principle of conservation of linear momentum, principle of conservation of angular momentum, principle of conservation of energy, and principle of conservation of charge. So charge is conserved. The principle says that the net charge on an isolated system is constant. The net charge on an isolated system is constant. Charge is conserved. Moving on. Charge is quantized. Charge is quantized means that the net charge on a system is integral multiple of E. And what is E? 1.6 into 10 raised to the power of minus 19 coulomb. One second, wait. Something happened to the internet connection. So we are working on it. Okay. Now I think I'm online again. Sure, beta. Now we are talking about force between multiple charges. How to write force between multiple charges? There is a principle called principle of superposition. The principle of superposition tells us that the force applied by one charge on another charge is independent of all the other charges present in the vicinity. However, the net force experienced by the charge is the vector sum of force due to each individual charge. Do realize force is a vector quantity. So when you are doing the addition, please do vector addition, don't do scalar addition. One useful result here is that if let's say there are 2 forces, if there are 2 forces F inclined to each other at angle theta, notice that I have made both the forces of same magnitude, then the F resultant comes out to be nothing but 2F cos theta by 2. This result becomes really useful in these type of question. So if you have got 2 forces of same magnitude F inclined at angle theta with each other, then the resultant is nothing but 2F cos theta by 2. So let's move on. When you have to write force on one charge due to multiple other charges, then just write force due to each individual charge, and force act along the line joining the charges. For like charges, force is repulsive. For unlike charges, force is attractive. So just like the force on one of the charge due to all the other charges, and then add up the force vectorially, because force is a vector quantity. Now we are going to talk about electric field. We say that a charge in the three-dimensional space around it creates electric field. This electric field, when interact with another charge, it applies a force on other charge. So we don't say that one charge applies force on another charge. No, A charge creates field and then that field applies force on the other charge present. If we have a point charge Q, if the charge is positive, the field due to the charge is radially outward. If the charge is negative, then the field created by this charge will be radially inward. The force experienced by a charge kept at position R is nothing but the charge you are keeping at that position times the field at the position of that charge. Now here, one important thing to take, this small thing people miss out. The electric field at a point is defined as the force acting per unit charge, given that the charge tends to zero. The field at a point is defined as force acting per unit charge, given that the charge you are keeping at that position tends to zero. What you need to understand here is that, let's say we have already a positive charge, and we wish to know what is the field due to this positive charge at a point P in space. To determine the field due to this positive charge at a point P in space, let's say we have kept another positive charge at point P. What will happen? These two charges will repel each other. Now, once the two charges repel each other, separation between them will increase. So the force acting between them will be less than what it should have already been. As the separation will increase from, let's say, initial R to final R dash, whatever force would have acted for separation R, now the force will act less than that. Since the force will act less than that, the field you compute here will be different. So what I am saying, this is essential that when we define field at a point, which is force acting per unit charge, the charge you have kept at that position should be very small. So moving on. Next heading we have to take care of electric field due to system of charges. Just like electrostatic force follows the principle of superposition, so does electric field. We say that electric field at a point due to multiple point charges. And then do realize that electric field is a vector quantity, just like force. So when you are finding the net electric field at a point, do the vector summation. If you have one single point charge, Q, then at a distance R from it, the field due to this point charge is nothing but KQ by R square. So if you have a point charge Q, then at distance R from it, field due to this point charge is KQ by R square. If the charge is positive, field is away from it. If the charge is negative, field is towards it. A positive charge creates field away from it. A negative charge creates field towards it. Moving on. So beta, how do you write field due to a simple point charge? A single point charge field is KQ by R square. Due to positive charge, away. Due to negative charge, towards. How do you find field at a point due to multiple charges? If you have to find field at a point due to multiple charges, write the field due to every single individual charge and add it vectorially, because field is a vector quantity. Moving on. Same thing they have done. Field due to one charge, second charge. So see, the net field is nothing but the vector sum of field due to every single individual charge. Then there is a heading. Physical significance of electric field. Why do we define electric field at the very first place? Here they have written a small line that if we do not assume the field, and we say that if there is a charge Q1, there is a charge Q2, then the force acting between them will be KQ1 Q2 upon R square. And we do not bring this field view that a charge creates field and that field applies force on another charge. If we do not bring this picture, for example, see, what we say in the field world is that if there is a point charge Q1, there is a point charge Q2, separated by distance R. The field picture says that the charge Q1 doesn't know that Q2 exists in space. The charge Q1 creates an electric field k q1 by r square at position of the second charge. And the second charge experiences a force. How much? Second charge q2 into field created by first charge at position of second charge. Hence, the Coulomb's law, k q1 q2 upon r square. Similarly, the field theory says that second charge doesn't know that first charge exists. A charge q2 creates an electric field k q2 by r square at position of first charge, due to which the first charge experiences a force. How much? q1, the first charge, into the field created by second charge at the position of first charge. So what does this heading tells us? The name of the heading is physical significance of electric field. If let's say there is one charge and there is another charge, if we don't define field at all, and we say that the force acting between two charges is k q1 q2 by r square, somebody might ask, okay, the force acting between two charges is k q1 q2 upon r square, but how much time does it take for the force applied by one body on another body to change, given that you shift a body? If I move first body from its original position to next position, does the force acting on second one change instantaneously, or does it take some time? Answer is it takes some time. When you move the first body from its position, the field created by first body at position of second body changes after some time, because if the field due to first body at position of second body changes instantly, then on moving the first body, instantly you will know that the force on second charge has changed. If the force on the second charge changes instantly, then we have got a method to transfer the information faster than the speed of light. And we know that nothing travels faster than speed of light. That's why the first charge creates a field. This field travels at speed of light. When you shift the first charge, the force experienced by second charge changes after some time lag. Okay, same question is asked in gravitation as well. Question is asked, what if sun suddenly disappear? If sun suddenly disappear, the force experienced by earth will change suddenly or will change after some time. So since we know that light takes 8 minutes 20 seconds to reach earth, if sun disappears suddenly, for the first 8 minutes 20 seconds, earth will keep on moving on the same orbit as if sun is still there. After 8 minutes 20 seconds, the earth will stop experiencing force of sun, and then earth will move in a tangential direction. Moving on. Now here one question is important, that an electron falls through a distance of this in an electric field of magnitude this. The direction of electric field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case. Contrast the situation with the free fall under gravity. Same question is given in NCERT, or more or less same question has been asked already in NEET. Now what I'm saying is, if you keep a charged particle in an external field, then the force experienced by the charged particle is nothing but charge times electric field. And the acceleration of the charged particle is nothing but this force acting on it divided by mass of the charged particle. Now, since we know that mass of proton is greater than mass of electron, you tell me who will experience a greater force when left in the same field. So point is that the force experienced by both of them will have same magnitude because the charge is same. So who will experience greater force when left in a field, proton or electron? Same, not same, equal and opposite, because the charge on both of them have same magnitude. Who will have greater acceleration? Since mass of electron is nearly 1800 times smaller, the acceleration of electron will be nearly 1800 times larger. So electron has way greater acceleration than proton. So electron travels this distance way faster than the proton. on बच्चों. Next heading is electric field lines. Electric field is a physical quantity. Electric field lines are imaginary construct. So if you have a positive charge, we assume electric field lines are going away from it. Here, some property of electric field lines we should know. Two electric field lines never intersect each other. Two electric field lines never intersect each other. The region of space where the electric field lines are closer to each other, like here, represents the region of stronger field. So if they ask at point A field is stronger or at point B, so you will say that the magnitude of electric field at point A is more than the magnitude of electric field at point B. The region of space where electric field lines are more close to each other, that represents the region of stronger field. So if they tomorrow draw a diagram like this, where is the electric field strong, at P or at Q? So you will say the region of space where the field lines are closer to each other, that's the region of stronger field. So electric field at P will be more than electric field at Q. Again, same thing. A positive charge creates electric field away from it. Okay? And the negative charge creates electric field towards it. Here, four important property. I am taking them one by one. Electric field line starts from positive charge and end at negative charge. Electric field lines originate at positive charge and they terminate at negative charge. If there is a single charge, there may start or end at infinity. So for example, in this diagram, this is a negative charge, field lines are coming towards it. From where the field lines are coming? They are coming from infinity. Okay, so that's what they are saying. If there is a single charge, they may start and end at infinity. Next point, beta. In a charge-free region, means where you don't have charge, electric field lines can be taken to be continuous curves. Electric field lines originate at positive charge, terminate at negative charge. So if you do not have any positive or negative charge, then the electric field line can't just terminate. Okay, it has to be continuous. Electric field lines originate at positive charge, they terminate at negative charge. So in a region of space which is charge free, electric field line has to be continuous. It can't suddenly, abruptly stop here. Because if the electric field line got terminated here, here must be a presence of negative charge. And they can't suddenly start from a point without the presence of any charge. If it starts from here, here you must have positive charge. So to this point is important, that in a charge-free region, electric field lines are continuous curves. Next, two field lines can never cross each other. If they did, the field at that point of intersection will not have a unique direction, which is absurd. So remember that two electric field lines can never intersect each other. Next point, electrostatic field lines do not form any closed loop. Now, as the course will proceed, I will talk about another type of electric field. Remember that there are two sources of electric field. One, charge. Second, time varying magnetic field. There are two sources of electric field. One is charge, one is time varying magnetic field. The type of electric field created by charge is conservative in nature. Conservative in nature. It means that they do not form a closed loop and the work done by them in a closed loop is zero. While the electric field created by time varying magnetic field, they always form a closed loop and the work done by them is non-conservative in nature. So once more, what do you have to remember? There are two types of electric field. One created by charge, one created by time varying magnetic field. the electric field created by charge originate at positive charge, terminate at negative charge, do not form a closed loop. When I say do not form a closed loop, what does it mean? Dekh betu. Look here. In this diagram, electric field lines originate at positive charge, they terminate at negative charge. Somebody might say, sir, this is to a closed loop now. No, betu, this is not a closed loop. It is not coming back. See, in diagram, it's only going from positive to negative. So the electric field created by charge originate at positive charge, terminate at negative charge, do not form a closed loop and is conservative in nature. That is why the work done by such a field in a closed loop is zero. Which electric field I am talking about? The electric field created by a charge. There is another type of electric field which is created by time varying magnetic field. The electric field created by time varying magnetic field, that forms a closed loop and is non-conservative in nature. It means that the work done by it in a closed loop is non-zero. So get it back. Next heading is electric flux. Electric flux represents the number of field line crossing a given area. Here the keyword is crossing. The more the number of field line cross, you say higher is the flux. The less the number of field line cross, you say lower is the flux. So electric flux represents the number of field lines crossing an area. Now, we have to talk about here in electric flux the basic definition of it. Beta see. One second, it's loading. It's not clear. 1 second. Now loaded. See what? The small flux linked with a small area is electric field vector at the position of area dot infinitely small area vector. Okay, we get flux from dot product of what electric field and area vector. The net flux comes out to be magnitude of electric field into magnitude of area vector into cos of the angle between electric field and area vector. Look here. Do realize for a closed surface, Gauss law works on a closed surface. For a closed surface, the area coming out of surface and normal to the surface is the direction of area vector. So this n cap is the direction of this infinitely small area vector. We get flux from dot product. Flux is a scalar quantity. Moving on. Here betu, see. The total flux coming out of a surface is addition of all the fluxes linked with every infinitely small area. So total flux coming out of surface is sum of all the flux with every small area. Now we have to talk about electric dipole. A pair of equal and opposite charges separated by some distance constitute a dipole. Then we define a quantity called dipole moment. Remember this, that if there is a charge minus q and there is a charge plus q, and the position vector of plus q with respect to minus q is r. Okay? Whose position vector? You are writing position vector of plus q with respect to minus q. Then the dipole moment is defined as charge times position vector of positive charge with respect to negative charge. Dipole moment is defined as charge times position vector of positive charge with respect to negative charge. So a very basic question I am asking. Let's say you have two charges of 4 coulomb and minus 4 coulomb. The 4 coulomb charge is kept at 2, 1, 3 and minus 4 coulomb charge kept at 0, 2, 2. Question is find the dipole moment of the system. So to charge is how much? 4. Now tell me what is the position vector of positive charge with respect to negative charge. So you have to do this minus this or this minus this. When I have just drawn the figure, I drew it from minus q to plus q. So the vector originated at minus q and the vector terminated at plus q. So final position is of plus q, initial position is of minus q. Final minus initial. Final minus initial. Finally you are at plus q Initially you are at minus q. So when you do final minus initial, what you get is 2i cap, 1 minus 2 minus j cap, 3 minus 2 plus k cap. Hence the dipole moment comes out to be 8i cap minus 4j cap plus 4k cap. Okay, but let's move on. The field of an electric dipole. First thing, remember here, Betu, there is no point in space where the field created by an electric dipole is zero. An electric dipole, when I show like this means negative charge, this means positive charge. There is no point in space where the electric field due to a dipole is zero. There no null point exists due to a pair of equal and opposite charge. A pair of equal and opposite charge create electric field at every single point in space. Now here, first thing we are trying to find, what is the electric field due to a dipole at a point on its axis? So we are directly going to the result. At a point on the axis of dipole, electric field is 2 k p by r cube. Notice that they have written in the vector notation. So if you have a short dipole, yes sir, of dipole moment p, then the electric field at a point on its axis at distance r is given by 2 k p by r cube. Electric field is a vector quantity, Betum. So whenever you are talking about electric field, you have to think of both magnitude as well as direction. So at a point on the axis of dipole, the direction of electric field is same as that of dipole moment. Notice here, I have drawn the dipole towards right, as well as at this point, I have drawn the electric field towards right. So tomorrow, if let's say you have dipole pointing this way, then the electric field at a point on its axis will be in same direction, whether there or whether here. So at a point on the axis of dipole, the direction of electric field created by dipole is same as that of dipole moment. How much, Betu? Magnitude how much? 2 kp by r cube. Keep mugging it up right now. Magnitude how much? Magnitude how much? 2 kp by r cube. Direction what? Same as the direction of dipole moment. Okay? Moving on. Electric field at an equatorial point. So if this is dipole, then what is the electric field at an equatorial point? At an equatorial point, the direction of electric field is opposite to that of dipole moment. Equatorial point is called equatorial point because this point is at same distance both from negative as well as positive charge. So at a point on axis, direction of electric field is same as that of dipole moment. At an equatorial point, direction of electric field is opposite to the dipole moment. At an equatorial point at distance r from a short dipole, the direction of electric field is opposite to the dipole moment, and the electric field is nothing but kp by r cube. Kp by r cube. So if you have a short dipole on the axis, 2 kp by r cube, same direction. On the equatorial line, half of that magnitude, kp by r cube, but in opposite direction. Moving on, bachcho. Dipole in a uniform electric field. I tell it to kids, this is one of the most important heading. What we do? Dipole in uniform electric field. Here you have to remember 4 points. First, if you keep a dipole in uniform electric field, then the force experienced by the dipole is zero. Why? Let's say there is a uniform electric field. Field is the same everywhere. Positive charge will experience force in direction of field. Negative charge will experience force in direction opposite to field. Both the charges have same magnitude. Field is uniform everywhere. So what is the net force? So positive experience force in direction of field, negative experience force in direction opposite to field. So these two forces will cancel out each other. They are in opposite direction. Net force acting on dipole in a uniform electric field is 0. Second point, the torque acting on dipole in uniform electric field is P cross E. You have to remember all these formula. Do realize torque is a vector quantity, dipole moment is a vector quantity, field is a vector quantity. If you are getting torque from the multiplication of dipole moment and electric field, you must have to do cross product. So torque equals to P cross E. Third thing. So first we learned force is 0. The force acting on a dipole in uniform electric field is 0. Second, torque acting on dipole in uniform electric field is P cross E. Third, potential energy of dipole in uniform electric field is given by minus P dot E. Notice that energy is a scalar quantity, right? So you will get energy from the dot product. Torque is a vector quantity. You get torque from the cross product. And you write this potential energy also as minus P E cos theta. What is theta? The angle between the electric field and the dipole moment vector. This angle is the angle theta. So moving on. Now here they are talking about what is the meaning of continuous charge distribution. What is the meaning of distribution over a line charge? What is the meaning of distribution of charge over a surface? So this is nothing great. Don't worry. Question won't come from here. Then we have something called Gauss law. Gauss law tells us that the net electric flux coming out of a closed surface, the net electric flux coming out of a closed surface equals to total charge within the closed surface divided by epsilon naught. Once more, the net electric flux coming out of a closed surface equals to total charge inside the closed surface divided by epsilon naught. Notice that here we don't talk about shape of surface, size of surface, location of charge inside surface, as well as outside charge. So we simply say, if there is a Gaussian surface and within the Gaussian surface, let's say we have got 2 point charges Q1 and Q2, then we will say that the net electric flux coming out of this closed surface is nothing but Q1 plus Q2 by epsilon naught. Here, realize that the flux coming out of this closed surface is independent of shape of surface, again repeating, size of surface, whether it's big or small, location of charge inside surface. If I move this charge Q1 a little bit from here to here, still the flux link will be same, as well as outside charge. So if you have an outside charge Q3, then there is no effect of Q3 with the flux of this surface. Do realize, when we are writing flux, we write the flux as closed integral of E dot ds. This electric field in the expression is the net electric field at a point on the surface due to both inside charges as well as outside charges. Okay, Betu? So what we have learned? The net electric flux coming out of a closed surface equals to Q in by epsilon naught. This Q in is the total charge inside the Gaussian surface, right? The flux linked with a Gaussian surface is independent of shape of surface, size of surface, location of charge inside surface, as well as outside charge. Do realize that the electric field at a point on the surface depends on both inside charge as well as outside charge. Here Q is the total charge enclosed by the surface S. Now, Beto, Gauss law is true for any closed surface, no matter what is the shape or size. Okay? The term Q on the right hand side of the Gauss law includes the sum of all the charge enclosed by the surface. The charges may be located anywhere inside the surface. Third point, in the situation when the surface is so chosen, then there are some charges inside and some outside. The electric field whose flux appears on the left hand side of equation is due to all the charges, both inside and outside us. The term Q on the right hand side of Gauss law, however, presents only the total charge inside. So when we are writing electric field at a point on surface, that is due to both inside as well as outside. But the flux is linked only with the charge inside. Beto, now here. This point, kids don't like. Listen to me. The surface that we choose for the application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care to let the Gaussian surface not pass through any discrete charge. Because if you have a point charge, then at the position of point charge, the field is not defined. Okay, so Gaussian surface shouldn't contain a discrete charge. Okay, same thing written, what I just said. Gauss law is often useful towards much easier calculation of electrostatic field when the system has some symmetry. Using Gauss law, we can find at a point field due to a point charge, line charge, sphere. But you can use Gauss law to determine the strength of electric field only when the field is symmetric. Finally, Gauss law is based on inverse square dependence distance contained in the Coulomb's law. This point is really, really important. Gauss law will fail if the field is not proportional to 1 by r square. Gauss law works because the electric field created by a point charge at a distance r from it is given by kq by r square. So this is important point, Beto. Listen. Finally, Gauss law is based on the inverse square dependence on the distance contained in the Coulomb's law. So Gauss law works because field is proportional to 1 by r square. Chalo beto, let's move on. Application of Gauss law. First application, that they have taken a line charge. Remember formula directly here. If you have a line charge of charge per unit length lambda, then at a distance r from it, the electric field due to this line charge is given as 2k lambda by r. Electric field due to a line charge at a distance r from it is given by 2k lambda by r. If the line charge is positive, it creates field away from it. If the line charge is negative, it creates field towards it. Notice that here field and distance are inversely proportional. So if I plot the graph of electric field due to a line charge versus the distance from it, what do we get? Rectangular hyperbola. Okay, so just remember this formula, electric field due to a line charge is 2k lambda by r. 2k lambda by r. 2k lambda by r. Remember it right now. By the way, fun fact. If you have a half ring with charge per unit length lambda and having a radius r, electric field due to that also at center, electric field is vector quantity, beta, hai na? Is also 2k lambda by r. So whether you have a line charge and you go at distance r from it, electric field is 2k lambda by r. If you have a half ring having charge per unit length lambda and radius r, electric field due to that also is 2k lambda by r. Moving on. Field due to uniformly charged infinite plane sheet. So if you have got this infinitely large plane sheet having charge per unit area sigma, then the electric field due to this comes out to be sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Field due to a point charge proportional to 1 by r square. Field due to a line charge proportional to 1 by r. Field due to an infinitely large plane sheet is independent of r. You can't find any r here, right? So remember that the field created by an infinitely large plane sheet of charge per unit area sigma is nothing but sigma by 2 epsilon naught. Notice that this result is independent of distance of the point from the surface of the sheet. Okay? Field due to uniformly charged thin spherical shell. When you have to write field due to a shell outside the shell, remember this line? When you have to write field due to a shell outside the shell, just keep the entire charge of shell at its center. When you have to write field due to a shell at a point outside the shell, just put the entire charge of shell at its center. And if you visualize that this entire charge is kept at center Q, then the electric field due to it at this point will be nothing but KQ by R square. So field due to a shell for outside point, just put the entire charge at center. Then they are talking about inside the shell. Remember that field inside the shell due to shell is 0. Field inside the shell due to shell is 0. Okay, and for outside point, put the entire charge at center. So if you have a shell of radius r, for any point at distance from center less than radius, the electric field comes out to be 0. For any point outside, for r greater than r, electric field is nothing but KQ by R square. If we plot the graph of this field versus the distance, inside to beta 0. So when you plot this graph from 0 till r, you don't find any field. And for outside point, field is inversely proportional to R square. Moving on. With this, our first chapter has been concluded. So see, Betu, I know there are many a formula, many a things, but the most important ones are the one given in NCERT. That's why we are focusing on those formula only. So which formula did we learn in this chapter? Fast I am saying. How do you write electric field due to a point charge, Bachchan? Electric field due to a point charge? Due to a point charge Q at distance r from it, electric field is KQ by R square. If this point charge is positive, it creates field away from it. If this point charge is negative, it creates field towards it. Then we have learned field due to a dipole. If you have a short dipole, then at a point on its axis, the direction of field is same as that of dipole moment. And how much field, Betu? 2kp by rq. And at an equatorial point, the direction of electric field is opposite to dipole moment. And here the electric field comes out to be how much? Kp by rq. Okay, bacha? Then, if you have a line charge, having charge per unit length lambda, then at distance r from it, electric field is how much? 2k lambda by r. K is 1 by 4 pi epsilon naught. And last one, if you have an infinitely large plane sheet having charge per unit area sigma, then the electric field due to it is nothing but sigma by 2 epsilon. So this covers all the formulas which are important in the first chapter. Field due to a point charge, kq by r square. Field due to dipole at a point on its axis, 2kp by rq. Field due to a short dipole at an equatorial point, kp by rq. Field due to a line charge, 2k lambda by r. Field due to an infinitely large plane sheet, sigma by 2 epsilon. So with this, let's move on to the second chapter. Electrostatic, potential and capacitors. So first is introduction, we are not worrying it. Now, a positive test charge, a test charge Q greater than 0, is moved from point R to point P against a repulsive force on it by the charge Q, which is again positive, placed at the origin. So here, the first and most important thing that we need to understand in this whole chapter is the definition of potential. Remember this line, and this is very, very important line. Change in potential energy is minus times the work done by conservative force. Change in potential energy is minus times the work done by conservative force. Electrostatic force is a conservative force. If the work done by conservative force is positive, then change in potential energy is negative. And if the work done by conservative force is negative, then the change in potential energy is positive. If you have one positive charge already, Hanji, and you move another positive charge close to it, okay, then when you are moving the second charge towards the first charge, in which direction first charge will apply force on second charge? They are applying repulsive force here. And what will be the direction of displacement? You are moving it towards. So force is radially outward, displacement is radially inward. If the force is radially outward, displacement is radially inward, the work done, which is given by force dot displacement, will be negative. And when the work done by conservative force is negative, change in potential energy is positive. So first thing in this chapter you have to remember is change in potential energy is minus times the work done by conservative force. That's what all I'm saying. And there are two positive charge. If you move one positive charge close to another positive charge, force is radially outward, displacement is radially inward, angle between force and displacement is 180. So work done by conservative force is negative. If the work done by conservative force is negative, then the change in potential energy is positive, potential energy increases. Then let's move on. Same thing saying, change in potential energy is minus times the work done by conservative force. Here, important point. The change in potential energy, the right hand side of equation, they are saying, the right side of equation 2.2 depend only on initial and final position of the charge. It means that the work done by an electrostatic field in moving a charge from one point to another depends only on initial and final position and is independent of path taken to go from one point to another. This itself tells you that electrostatic force is conservative in nature. Now, baby, let's move on. Equation 2.2, the same equation, defines potential energy difference in the term of physically meaningful quantity work. Okay? The potential energy difference between 2 points is explained in the term of work. Now moving on. We define electrostatic potential. Where to focus here? What is force to field? What is force to field? Means field is nothing but force acting per unit charge, na? What is force to field in the vector world? Same thing is potential energy to potential in the scalar world. Potential energy, potential, both are scalar quantity. Force, electric field, both are vector quantity. So we define the potential at a point as the change in potential energy in bringing a test charge from infinity to the point per unit charge. What is beta potential at a point? Change in potential energy per unit test charge in bringing a test charge from infinity to the point. So change in potential energy per unit charge. This is the potential of a point. One more time. What is force to field in the vector world? Same thing is potential to potential energy in the scalar world. Again, they are trying to say that no matter what is the path you take, since electrostatic force is conservative, the change in potential on going from R to P, all the path is same. Now here, first formula that we have to remember. If you have a point charge Q, then at a distance R from it, if you have a point charge Q, then at a distance R from it, potential comes out to be KQ by R. Potential is a scalar quantity, no header. Field is a vector quantity. While adding a field, you have to do vector addition. Potential is a scalar quantity. You can simply write potential due to multiple charge and add it up. Now moving on, bachcho. Potential due to a point charge. We have just done potential due to a point charge comes out to be how much? KQ by R. KQ by R. This brings one more interesting and important relationship. Let's say there is a point charge Q. At a distance R from it, the field due to the charge, field is a vector, but I am just writing the magnitude. Field due to it will be KQ by R square. And potential due to it will be nothing but KQ by R. You can think of this field as, think of this KQ by R square as KQ by R into 1 by R, and this part becomes potential. So the field at potential created by a point charge at a point have this relationship, that the magnitude of electric field equals to magnitude of potential divided by R. Magnitude of electric field equals to magnitude of potential divided by R. Moving on. But this graph is important. In this graph, maybe not visible, I am zooming in. This graph shows how does the electric field vary with distance and how does the potential vary with distance. Focus here, bachcho. Electric field due to a point charge at distance r from it is given by kq by r square. Field is inversely proportional to r square. So when distance becomes double, field becomes 1/4. When distance becomes triple, field becomes 1/9. If I make this denominator, let's say, to 2 times, you will get 2r whole square. So an extra term of 4 in the denominator. So when distance becomes double, field becomes 1/4. When distance becomes triple, field becomes 1/9. If you look at the formula of potential, potential is kq by r. Here when distance becomes double, potential becomes half. Distance becomes triple, potential becomes 1/3. So question is, who drops faster as you go away from the charge? Field is proportional to 1 by r square and potential is proportional to 1 by r. Notice here, field drop faster compared to the potential because at double the distance, potential becomes half, but field becomes 1/4. So field drops faster than the potential. Now let's move on, bacho. Potential due to an electric dipole. Directly formula we will learn. If you have a short electric dipole of dipole moment P and you wish to write what is the potential due to the short dipole at a point in space whose position vector is r and this angle is theta, then the potential due to dipole, I am not talking about field, I am talking about potential, scalar. Potential due to dipole at that point will be nothing but Kp cos theta by r square. How much, bachcho? Kp cos theta by r square. Kp cos theta by r square. Mark it up right now. Kp cos theta by r square. Kp cos theta by r square. If they ask you what is the potential at an axial point, then for an axial point, theta will become 0, cos 0 will become 1. So due to a short dipole of dipole moment P at this point in space whose distance is r, the potential simply comes out to be Kp by r square. Okay, beto? Let's move on. Keep remembering all formula fast. We are not going into the derivation now. Important point. First, the potential due to a dipole not just depend upon r but also on the angle between the position vector r and the dipole moment vector p. So it depends upon r as well as it depends upon the choice of theta. It is, however, actually symmetric about p. What is the meaning of it? If this is the dipole, here you think of a point. Now think of a cone. All the point on this circle will be at same distance and they will have same angle. Since they are at same distance and have the same angle, then at all these point potential will be same. This is the first point. Second point, the electric dipole potential falls off at large distance as 1 by r square, not as 1 by r. So we know that if we have a point charge q, then at a distance r from it, potential is kq by r square. And if we have a short dipole of dipole moment P, then at a distance r making angle theta, the potential is given by Kp cos theta by r square. So that's what they are trying to say, that the potential varies proportional to 1 by r square, not proportional to 1 by r as for a point charge. Now, how do you write potential at a point due to system of charge? Remember this line, betu? Potential also follows principle of superposition. If you have to write the potential at a point P due to multiple charges Q1, Q2, Q3, Q4, Q5, then simply write the potential due to each individual charge and add. Since potential is a scalar quantity, what you have to do here is the scalar addition. So we say that the potential at point P is nothing but KQ1 by R1P plus KQ2 by R2P plus KQ3 by R3P plus KQ4 by R4P plus KQ5 by R5P. So potential at a point due to a system of multiple charges is nothing but sum of potential due to each individual charge. Potential is a scalar quantity, so finding the potential due to multiple charges is easier. All you have to do is just add up the potential due to each charge. Now, Betu, there is a question. There are two charges and they are asking what is the potential at point P. Not a great thing. We can do it easily. Now, this question is important. This figure shows field lines due to positive and negative charge. Then they have asked at which point potential is more, P, Q, A, B, and if you move a positive charge from here to here, potential energy increases, decreases, or if a negative charge from here to there, potential energy increases, decreases. I mark this particular question as important. And remember, baby, here two lines. First, in direction of field, potential decreases. When you move in direction of field, potential decreases. In direction of field, potential decreases. One more time saying, when you move in direction of electric field, electric potential decreases. So Betu, tell me, in this first case, electric field lines are going from P towards Q or Q towards P? It's visible. Electric field lines are going from P towards Q. So potential at P has to be more than potential at Q. Look in this second diagram. Field lines are going from B towards A or A towards B. They are radially inward, the negative charge. So electric field lines are from B to A. In direction of field, potential decreases. When you move in direction of field, potential decreases. Field lines are from B to A to B. You can see that field lines are from B to A. So which one will have higher potential, A or B? So you'll say since field lines are going from B to A, potential at B is more than potential at A. Another thing, you have to understand potential energy associated with a charge kept at a point where potential is V is given by QV. Just like now, beta, force equals to QE. Potential energy equals to Q times potential. Sorry, I wrote this wrong. Force equals to QE. Then potential energy equals to charge times potential. Now listen, baby. VP is more than VQ, right? If you keep a positive charge for positive charge, when you multiply with VP, you will get big. When you multiply with VQ, you will get less. So for positive charge, if kept at P or kept at Q, potential energy at P will be more than potential energy at Q. Now ask yourself, -3 is more or -5 is more? -3 is more or -5 is more? -5 is more in magnitude, but we say that -5 is 2 less than -3. So if charge is positive, then potential energy at P will be more than potential energy at Q. But for negative charge, it will flip due to that minus sign. Then you will say potential energy at Q will be more than potential energy at P. Look here now in this question. Here potential is more where? At B than at A. Sir, how do you know? Remember, in direction of field, potential decreases. So if you keep positive charge, for positive charge, where the potential energy will be more? Sir, for positive charge, potential energy will be more at the place where potential is more. So for positive charge, potential energy at B will be more than potential energy at A. And for negative charge, potential energy will be less where the potential is more because of the minus sign. -3 is more or -5 is more. So you will say for negative charge, potential energy at A will be more than potential energy at B. I have just said one of the most important thing, focus on this. When you move in direction of field, potential decreases. This line you have to remember. When you move in direction of field, potential decreases. Or you can think over it this way, this whole line. Electric field lines are from positive charge to negative charge or negative charge to positive charge. All of us know that electric field lines are from positive charge to negative charge. In the vicinity of positive charge, at a point nearby positive charge, whose potential dominance will be more? Sir, the one whose distance is less. So in the vicinity of positive charge, the potential will be positive. While in the vicinity of negative charge, potential has to be negative. So electric field lines are from high potential, where it's positive, to low potential, where it's negative. So I have just said before moving on, again repeating one more time. Beto? In the direction of field, potential decreases. In the direction of field, potential decreases. So which one is at higher potential, P or Q? So since field lines are going from P to Q, potential at P is more than potential at Q. A positive charge has more potential energy where the potential is more. A positive charge has more potential energy where the potential is more. A negative charge has more potential energy where the potential is less. Similarly here, electric field line is from B to A. B will have more potential than A. So if you are keeping positive charge, potential energy at B is more than potential energy at A. But if you are keeping negative charge, then the potential energy at A is more than potential energy at B. Chalo bachcho, let's move on. What are equipotential surfaces? Collection of all the points which are at same potential. Those are called equipotential surfaces. Equipotential surfaces due to a point charge are sphere. Equipotential surface due to a line charge, coaxial cylinder. Equipotential surface due to a plane are plane parallel to the plane. Okay. For a uniform electric field, equipotential surfaces are plane perpendicular to the field. For a uniform electric field, equipotential surfaces are plane perpendicular to the field. Now, potential energy for system of charges. Focus here, bachcho. If you have got 2-point charges Q1 and Q2 separated by distance R, if you have got 2-point charges Q1 and Q2 separated by distance R, then the potential energy associated with it is K Q1 Q2 by R. If you have got 2-point charges Q1 and Q2 separated by distance R, then the potential energy associated with it is K Q1 Q2 by R. Notice that for like charges, either both will be positive or both will be negative. For like charges, potential is positive. Potential energy is positive. For unlike charges, when one is positive, one is negative, potential energy is negative. Moving on. Potential energy in an external field. This we have already taught. If you have a dipole, a point charge, then the potential energy of this charge in an external field V is nothing but charge times potential at that point. The potential point charge is charge times potential at that point. Moving on. Potential energy of system of two charges in external field. So if you have got two charges, better focus. If you have got two charges, then you have to write potential energy due to the first charge. Charge times potential at the position of first charge, plus potential energy due to second charge. Second charge times potential at position of second charge. Plus you have to write the potential energy due to their interaction, K Q1 Q2 by R. So we have to write three terms. Okay. Potential energy of a dipole in an external field. This I have just said. Torque is P cross E. Torque is P cross E. And the potential energy is minus P dot E. Torque is P cross E. Potential energy is minus P dot E. Then we have got electrostatics of conductor. This is important heading. Focus on all the points one by one. First point. Inside a conductor, electrostatic field is zero. Inside a conductor, electrostatic field is zero. Any theoretical question can come from these points. So we say, if you have a conductor and you keep it in an external electric field, charges get induced on the surface of conductor, making the net electric field in the flesh of conductor zero. the net electric field in the flesh of the conductor under electrostatic condition when the charges are not moving, under electrostatic condition is 0. First point. Second point, at the surface of a charged conductor, electrostatic field line must be normal to the surface at every point. Why? Better focus. We know that field potential relation is E equals to minus del V by del R. If in a region of space electric field is 0, electric field is absent, then in that region of space, the change in potential will be 0. Think of it just like acceleration equals to dv by dt. If acceleration is 0, you will say velocity is constant na beto. Similarly, if field is 0, previous year, NEET question, very important. If field is 0 in a region of space, then the potential of that region of space is constant. Okay. So here, remember this point. Under electrostatic condition first. First, electric field in the flesh of conductor is 0. Since electric field is 0, potential of all the points is same. Since potential of all the points is same, the surface of a conductor acts like an equipotential surface. Okay? And then, since the surface of conductor acts like an equipotential surface, electric field must be normal to equipotential surface. Electric field must be normal to equipotential surface. Let's say, beta, this is a surface. And let's say at all points on this surface, potential is 10 volt. It means that on moving along the surface, potential is not changing. And we have just learned that on moving in direction of field, potential decreases. So if you go from 2 points, from one point to another point on this surface, as you move from, let's say, point A to point B, on moving along the surface, potential is not changing. Why? Because it's equipotential surface. Hence, there can't be any electric field along AB. Entire electric field must be perpendicular to AB. So, remember this point about equipotential surface. Electric field lines are always normal to equipotential surfaces. Let's move on. The interior of conductor has no excess charge in the static situation. If you give any charge to the conductor, all the charge relies on its surface. So first point is that electric field in the flesh of conductor under electrostatic condition is 0. Second, electric field lines are always perpendicular to the surface of conductor. Third, if you give a conductor a charge, all the charge is found on its surface. Fourth, electrostatic potential is constant. Since field is 0, electrostatic potential is constant throughout the volume of the conductor and has the same value as inside and on its surface. Okay, these are the points we have to remember. Last point. Electric field at the surface of a charged conductor. If you have a charged conductor, then at a point just outside the surface, electric field is nothing but sigma by epsilon naught. So if you have a charged conductor, and here on the surface of this charged conductor, let's say here the local surface charge density is sigma. Then at a point just outside the surface of this conductor, electric field is nothing but sigma by epsilon naught. For sheet we got sigma by 2 epsilon naught. Here we get double of it, sigma by epsilon naught. Okay, beto? Let's move on. Electrostatic shield simply says that if you have a conductor with a cavity and you keep any charge within this cavity, if you have a conductor with a cavity and you keep any charge within this cavity, then due to an external charge, it won't experience any net force. Charge will get induced over the surface of conductor, which will cancel out any force applied by any external charge on it. So with this dielectric and polarization. Here what you have to remember, there are something called polar molecules and there are something called non-polar molecules. What are polar molecules? Polar molecules are the one which have a net dipole moment of each molecule. Polar molecules are the one which have a net dipole moment. Non-polar molecules are the one whose dipole moment is 0. But remember that even non-polar substance in the presence of external electric field becomes polar. Even non-polar substance in the presence of external electric field becomes polar. So here, when you deploy an electric field, the dipoles get aligned in the direction of electric field. On one side you get positive charge, on one side you get negative charge. When you keep a substance in external electric field, due to the induced charges, you get electric field in the opposite direction. In a conductor, the induced electric field exactly cancels out the applied electric field. That's why the net electric field inside a conductor is 0. But if you have a dielectric, then in that one induced electric field, if you have a dielectric, in this, the induced electric field is weaker than the applied electric field. That's why the net electric field inside doesn't become 0. Still some electric field exists. Polar molecules are the one which have a permanent dipole moment. H2 is non-polar, HCl is polar. But remember one line, in the presence of external electric field, even non-polar substance becomes polar. In the presence of external electric field, even non-polar substance becomes polar. So they are showing you first non-polar molecules. Here non-polar molecules, positive, negative are really close. If you deploy an electric field, let's say towards right, the positive will move towards right, negative will move towards left. Now there is some separation between this positive and negative charge. So this non-polar substance now have developed some dipole moment. Okay, and if you have got polar molecules, when you deploy electric field, they have the habit of aligning their dipole moment in the direction of field. So positive charge goes in direction of field, negative goes in opposite direction. Yeah, not much of formula is there. I'm not wasting your time. Let's move on. Then we have got capacitance. Where to focus first thing? What is the relation between charge on a capacitor, potential of the capacitor, and its capacitance? So we say Q equals to CV. Remember that the capacitance of a conductor is independent of both charge on the conductor as well as potential of conductor. The capacitance of a conductor is independent of both charge on the conductor as well as potential of conductor. It's a proportionality constant. So if you double the charge, then the potential becomes double. You triple the charge, the potential becomes triple. Capacitance remains the same. So remember the formula, Q equals to CV. Now most important way to here, parallel plate capacitor. The capacity of a parallel plate capacitor is epsilon naught A by D. The capacity of a parallel plate capacitor is epsilon naught A by D. What is A? The plate area. What is D? The separation between two plates. So the capacity of a parallel plate capacitor is epsilon naught A by D. They might ask, what will happen if you double the separation between the plate? So you will say, see, capacity is inversely proportional to D. You double the separation, capacity becomes half. So capacity of a parallel plate capacitor, epsilon naught A is what? Plate area by D. D is the plate separation. Effect of dielectric on capacitance. Again, important heading. But we will directly look at the final result. We say, remember it this way, capacity with the dielectric inside, subscript K, equals to dielectric constant times capacity without the dielectric. The capacity of a capacitance with the dielectric inside equals to dielectric constant times capacity without the dielectric. Okay? So if they ask you, a dielectric of dielectric constant 5 is kept between the plates of a capacitor, completely filling the space, what happens to the capacity? You will say that if you put a dielectric of dielectric constant 5, the capacity will become 5 times. So if the original capacity is, let's say, 12 microfarad, and you put inside it a dielectric of dielectric constant 4, completely filling up the space. So you will say if you put a dielectric of dielectric constant 4, then the capacity becomes 4 times, which is 48 microfarad. Moving on, bachcho. Combination of capacitor. Remember that combination of capacitor, reverse of like resistor. When you put multiple capacitor in series, 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3. And when you put multiple capacitors in parallel, then C equivalent is C1 plus C2 plus C3 and so on. Okay. So when you have got capacitors in series, what we get betu? 1 by C equivalent is 1 by C1 plus 1 by C2. If you have multiple, 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Capacitors in parallel, when you put multiple capacitors in parallel, then your simply capacity comes out to be C1 plus C2 plus C3 and so on. Energy stored inside a capacitor. Again, important heading, bachcho. Remember all the version. Energy stored inside the capacitor can be written as half CV square, can be written as Q square by 2C, can be written as half QV. I know that kids usually remember this, but if two capacitors are connected in series, they will have same charge. Let's say first one have capacity C1 and second one has capacity C2. Here to compare the energy, this formula is better because Q is same. So the one who has more capacity, let's say C1 is more than C2, then the energy stored in one will be less than energy stored in two, given that they are connected in series. And similarly, if two capacitors are connected in parallel, what will they have same? They will have same potential across them. So if let's say first capacitor has capacitance C1 and second has C2, now this time it's better to compare the energy using energy stored as half CV square. So since the potential is same across both of them, the one having more capacity will have more energy stored. Okay. So in series, who has got more energy stored? The one who has less capacitance. In parallel, which capacitor has more energy stored? The one who has more capacitance. So these formulas are important. Energy stored inside a capacitor, half CV square or Q square by 2C, or half into charge on the plate of capacitor times the potential drop across the capacitor. Then another formula is given. What is the electric field between the plates of a capacitor? So if you have got two plates, sigma minus sigma, the first plate create electric field sigma by 2 epsilon naught, second one create sigma by 2 epsilon naught. So the net electric field between the plate comes out to be sigma by epsilon naught. Notice this thing, the net electric field between the plates of capacitor is sigma by epsilon naught. In this net electric field, both the positive and negative plate contribute 50-50%. So half of this field is due to positive plate, half of this field is due to negative plate. Moving on. Beto next. This is important, energy density. Energy stored per unit volume in the form of electric field is given by half epsilon naught E square. Energy stored per unit volume. Beta, this is not energy. U is not energy. U is energy density. That's why they have used small u. Energy density. That is energy per unit volume. So energy density because of electric field is half epsilon naught E square. Moving on. With this, our second chapter is over. Now let's move on to third chapter, which is current electricity. Beto, first, average current is total charge flow upon total time taken. Total charge flow upon total time taken. So if 10 coulomb of charge passes in 5 seconds, what is the current associated? 10 by 5, which is 2 ampere. Current is total charge flow upon total time taken. Actually, it's average current, but okay. Now get back here. Instantaneous current is dq by dt. the infinitely small charge flow upon the infinitely small frame of time in which it flows, dq by dt. Then they are talking about electric current in conductors. No great formula here. Next formula our came is Ohm's law. The potential drop across a conductor is directly proportional to current flowing through the conductor. The potential drop across a conductor is directly proportional to current flowing through the conductor. Then we add up a proportionality constant which is R. This law is not followed by all material. This is called Ohm's law, and the material which follow this law are called ohmic conductors. Ohmic conductors. For ohmic conductors, the resistance is independent of the applied potential drop and current. Just like I just said, in Q equals to CV, the capacitance is independent of charge and potential. In ohmic conductor, the resistance is independent of applied potential drop and current. Keep it in mind. Yesterday's test question came from this part only. I will show. Okay, that will come little late. We will go there. Now, beto, what does the resistance depends upon? Next formula. The resistance depends upon length of the conductor, cross-sectional area of conductor, and another property of conductor which is called resistivity. Resistivity is intensive property. So if you have a big block of iron or a small piece of iron, resistivity of both is same. Okay, resistivity is intensive property. This is better resistivity. So we say that if we have a conductor of length L having a cross-sectional area A, the more the length, the more the resistance, the more the cross-sectional area through which the current flow, the less the resistance. And then this is a proportionality constant. Resistivity depends upon nature of material and temperature. Resistivity depends upon nature of material and temperature. Now, moving on. Beta, this is called Ohm's law in vector form. J equals to sigma E. J is current density, sigma is conductivity, E is the electric field. J equals to sigma E. This is current density. Sigma is conductivity. The reciprocal of resistivity is conductivity. So if resistivity is X, then conductivity is 1 by X. And times electric field. J equals to sigma E, another important formula. Now, we have to talk about something called drift velocity. Look here, Beto, first line. This statement tells you that the average velocity of an electron in a conductor is 0. Velocity, vector quantity. Some will have velocity here, some will there, some will there, some will there. The average velocity of an electron in a conductor is 0. Now, once you deploy an external electric field, each electron finds an acceleration. How much? Force on it. Force is charge minus E into electric field by M. So acceleration will be EE by M. Now, if you look at the velocity of any electron after time t, that will be initial velocity plus acceleration into time. Now, I am not going to waste your time here. We will directly reach the final result. So, what we get from here is, due to the application of electric field, the electrons on an average gets a velocity. This velocity is called drift velocity, and this velocity come out to be E tau by M. How to remember? See, Beto, there is an electric field E. Yes. So if you keep an electron, force on electron will be nothing but EE. Yes. So acceleration of electron will be EE by M. In magnitude, direction will be opposite. Don't care. Magnitude EE by M. We define something called relaxation time. Relaxation time is the mean time gap between two successive collisions. So by the time it will have next collision, due to this acceleration, it will gain a velocity. How much? Acceleration into time. So just remember formula. Drift velocities EE tau by M. Drift velocities EE tau by M. Drift velocities EE tau by M. Easy to remember. EE, this is force, magnitude of force. Divided by mass, this is acceleration into time. This is the drift velocity. Drift velocity is EE tau by m. Now, leave it, don't worry, move on. Mobility. Beto, higher the electric field you deploy, stronger the field you apply, more is the drift velocity. Okay? Drift velocity is directly proportional to electric field deployed, and the proportionality constant is called mobility. Mobility. Drift velocity equals to mobility times electric field. Drift velocity equals to mobility times electric field. Neither the mobility depends upon electric field applied, nor does it depends upon drift velocity. On doubling the strength of electric field, the drift velocity becomes double. So this is next formula which we have to remember. Drift velocity equals to mobility times electric field. Let's move on. Now, here they are talking about limitation of Ohm's law. From here the question came in yesterday's paper, where you can't apply Ohm's law. V ceases to be proportional to I. This was the first option. Second option, the relation between V and I depends upon the sign of V. In other words, if I is the current for a certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of same magnitude as I in the opposite direction. This is the IV characteristic curve of a diode. We know that for a positive potential of 0.2, you are getting some positive current, but for the same negative potential of 0.2, you don't get any negative current. So that's what this second point means, that on flipping the sign of V means if let's say earlier this is high potential, this is low, and now making this high and this low, you don't get the same value of current in the opposite direction. Third, the relation between V and I is not unique. It means that for multiple different voltages, you might find the same current. For multiple different voltages, you might find same current. So the statement is the relation between V and I is not unique. It's not that for a particular potential drop, you get a particular current. Now, resistivity of various material, temperature dependent on resistivity. Remember, bacho, for conductor, as temperature increases, resistivity increases. For semiconductor and insulator, as temperature increases, resistivity decreases. So once you start heating copper, its resistivity increases, its conductivity decreases. A copper is so awesome conductor at a lower temperature, but as you start heating copper or iron, which are good conductor in general, their conductivity decreases at higher temperature. So for conductor, as temperature increases, resistivity increases. For semiconductor and insulator, as temperature increases, resistivity decreases. Let's move on. Electrical energy power. All you have to remember is this thing. Power equals to IV. It works in all chapter. It works even in AC. Power into potential drop through which the current is flowing. Power equals to IV. Now, when you are writing power associated with a resistor, V can be written as IR, so power becomes I square R, or I can be written as V by R, so power can also be written as V square by R. For two resistors connected in series, current has to be same. So as to compare who dissipates more power, it's better to use power equals to I square R. In series combination, the one current will be same, the one which will have more resistance will dissipate more power. And in parallel combination, the one who will have more resistance will dissipate less power because R comes in the denominator. Cell EMF, internal resistance, not of use. Beto, remember this thing. When you draw a current I from a cell which has internal resistance R, then the potential drop across the terminal of cell is nothing but E minus IR. When you draw a current I from a cell who has EMF E and internal resistance R, then the potential drop across the terminal of cell is nothing but E minus IR. Cell in series and parallel. So first they have given series. In series, directly add up the EMF, directly add up the resistance. EMF equivalent is E1 plus E2 plus E3, and R equivalent is equals to R1 plus R2 plus R3. But notice, for this to done, I will write EMF equivalent as E1 plus E2, given that both the EMFs have same polarity. First EMF want left to be higher, second EMF want left to be higher. Then I will say the total EMF is E1 plus E2. If they would have given me this E2 like this, then I will say now the net EMF towards left will be E1 minus E2. But resistance always add up. So if this one has internal resistance R1 and this has R2, still internal resistance will be R1 plus R2. Moving on. So first, the equivalent EMF of series combination of N cell is just the sum of individual EMF, and the equivalent internal resistance of series combination of N cell is just the sum of their internal resistances. Now moving on, let's talk about parallel. If you have got two cells in parallel, then we to see R equivalent, just like formula of resistances in parallel. 1 by R equivalent is 1 by R1 plus 1 by R2. But in the E equivalent, rather than writing R equivalent here, I make it remember the formula this way. So for multiple cells in parallel, E equivalent is E1 by R1 plus E2 by R2. If you have more, then more, into R equivalent. So for cells in series, EMF simple sum, resistance simple sum, internal resistance simple sum. Just remember about the polarity. Okay. For multiple cells connected in parallel, 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3 and so on. E equivalent is E1 by R1 plus E2 by R2 plus E3 by R3. I wrote here R2. E1 by R1 plus E2 by R2 plus E3 by R3 and so on, multiplied by R equivalent. Chalo betu. Then we have got Kirchhoff's rules. First, junction rule. At any junction, the sum of current entering the junction is equal to sum of current leaving the junction. They might ask you, junction rule is based upon what? Junction rule is based upon principle of conservation of charge. Kirchhoff junction rule is based upon principle of conservation of charge. Second is loop rule. The algebraic sum of change in the potential around any closed loop involving resistor and cell in the loop is 0. So loop law says that once you go around any particular loop, the sum of all the potential drop add up to 0. Kirchhoff's loop law or loop rule is based on principle of conservation of energy. So better one more time. Junction rule depends upon what? Principle of conservation of charge. Loop rule depends upon what? Principle of conservation of energy. Here now we are talking about potential. If you add up all the potential across a closed loop, then the total sum comes out to be 0. Then there is a question, not of use, not of use. Don't worry. Don't worry. Then we have got Wheatstone bridge. You know that if R1 by R2 equals to R3 by R4, then this point B and D will be at same potential and no current will flow through this galvanometer. Once more, if R1 by R2 equals to R3 by R4, then point B and D will be at same potential and no current will flow through this particular galvanometer. With this, our third chapter, which is current electricity, is over. Now we will take a 5 minutes break. If you have to go somewhere to loo or something, go, come back. After 5 minutes, we will start with the fourth chapter. Okay, bachcho. So let's start with moving charge and magnetism. First introduction. A current carrying wire creates an electric field around it. In this first figure, the current carrying wire is coming out of the plane, dot. The magnetic field lines created by this current carrying wires are circular loop following right hand thumb rule. So align the thumb of right hand in the direction of current carrying wire and the fingers curl the way the magnetic field lines curl. Do understand that the tangent at a point on the magnetic field line gives the direction of magnetic field. So if you have this current carrying wire, let's say carrying current up, then curl the fingers of right hand around this current carrying wire. So let's say your fingers curl this way. At any point, the tangent will give the direction of magnetic field. Okay. So this shows wire is outward, and these are small magnetic dipoles kept, and they are showing how do the magnetic dipoles arrange. This blue part represents the north pole of dipole, and the white part represents the south pole of dipole. So if the current is outward, dipoles align this way because the magnetic field lines are anticlockwise. If the current is going in, align the thumb of right hand in direction of current. The way your fingers curl around your thumb of right hand, the same way magnetic field lines curl, and magnetic field lines will be clockwise. Now, magnetic force, source of field. A moving charge creates magnetic field. A charge at rest neither create magnetic effect nor experience any magnetic force. So who creates magnetic effect and who experience magnetic force? When the charge is moving. A charge at rest, electrostatic, only electric field. Okay, a moving charge creates magnetic field. Now here they are talking about comparison between electric and magnetic. Beta Lorentz force. The force experienced by a charge who is moving with velocity v at a place where magnetic field is B is given by force experienced by charge equals to Q into V cross B. Q into V cross B. Now here cross product comes. So you have to be very careful while doing the cross product. Moreover, in magnetism, Nabita, pay special attention to the nature of charge. If the charge is positive, the positive charge will experience force in direction of V cross B, while a negative charge will experience force in direction opposite to V cross B. So here they are talking about Lorentz force. Lorentz force is nothing but the sum of electric force, magnetic force. If you keep a charge at a place where the electric field is E, then the force experienced by charge is QE. If the charge is moving with a velocity V at a place where magnetic field is B, then the magnetic part of force will be Q into V cross B. So they have written the net force acting is QE plus Q into V cross B. Hence, taking Q common, what you get is E plus V cross B. Here, the first most important type of question created is that what is the condition for Lorentz force acting on a charge to be zero? So, if you want the Lorentz force acting on a charge to be zero, then this part E plus V cross B should be zero. Hence, E has to be equals to minus times V cross B. Hence, electric field has to be equals to A cross B is same as minus times of B cross A. Hence, electric field has to be nothing but B cross V. So, if the charge experience net Lorentz force 0, then E has to be same as B cross V. Okay, important result. Now, moving on. Here, important thing. Interaction with magnetic field, we find the following features. First, it depends on, magnetic force depends upon charge, velocity and magnetic field. Charge on the particle, velocity and magnetic field. Force on a negative charge is opposite to that on a positive charge. Force on positive charge in same direction as V cross B, negative charge opposite. The magnetic force Q into V cross B includes a vector product of velocity and magnetic field. The vector product makes the force due to magnetic field vanish, become zero if the velocity and magnetic field are parallel or anti-parallel. So if a charged particle has velocity in the same direction as that of magnetic field, then when we write Q into V cross B, the magnitude of V cross B is nothing but magnitude of V into magnitude of B into sine of the angle between them. If velocity and magnetic field are parallel, then theta is 0 and sine 0 is 0. If velocity and magnetic field are anti-parallel, then theta is 180 and sine 180 is also 0. So if the velocity is parallel or anti-parallel to magnetic field, then the magnetic force is 0. Next, the magnetic force is 0 if the charge is not moving. Okay? Only a moving charge feels the magnetic force. So a charge at rest neither creates magnetic field nor does it experience any force due to magnetic field. Now, Beto, here one point is missing, but I say this point is the most important point. Since you get the force from the cross product of velocity and magnetic field, so if the velocity and magnetic field lie in the plane of the board, then V cross B will be perpendicular to the plane of the board. So hence force is perpendicular to both velocity and magnetic field. The magnetic force acting on a charge is perpendicular to both velocity of the charge as well as magnetic field. Since force is perpendicular to velocity, when we do the dot product of force and velocity, what does the dot product of force and velocity gives? The dot product of force and velocity gives power. Since force is perpendicular to velocity, when we do the dot product of force and velocity, the dot product becomes 0, because in dot product you will write magnitude of F into magnitude of V into cos of the angle between them. Since force is perpendicular to velocity, here angle comes out to be 90 degree and cos 90 is 0. So very important case. Fourth thing. First, since you get the magnetic force acting on the charge from cross product of magnetic field and velocity, force is perpendicular to both magnetic field as well as velocity. Since force is perpendicular to velocity, F dot V is 0, hence the power is 0. Magnetic force can't do work. It can't deliver power. It can't change kinetic energy. Magnetic force can't do work. It can't deliver power. It can't change the kinetic energy. Remember this thing, huh? So which thing? I just said revising, fourth point. Since magnetic force comes from the cross product of magnetic field and velocity, V cross B, velocity and magnetic field. Magnetic force is perpendicular to both velocity as well as magnetic field. Since the magnetic force is perpendicular to velocity, F dot V is 0, power delivered by the magnetic force is 0. Magnetic force can't do work. Magnetic force don't change the kinetic energy, and hence magnetic force can't change the speed. Now, magnetic force on a current carrying conductor. Directly we are going at the result. The force acting on a current carrying wire is I into L cross B. I into L cross B. But a current is a scalar. So we take the direction of length same as the direction of current flowing in the wire. So if there is a wire, let's say carrying current from west to east, you will take this length vector from west to east. If there is a current carrying wire carrying current up, you will take the length vector up. So the force acting on a current carrying wire placed in a uniform magnetic field is given by I into L cross B. F equals to I into L cross B. F equals to I into L cross B. Okay? Motion of charge in magnetic field. So here they have explained the same thing. One second, I moved too fast. Wait to this. If you project a charged particle perpendicular to magnetic field, if you project a charged particle perpendicular to magnetic field, then the radius in which the charged particle does circular motion, that radius is nothing but mv by qb. That radius is nothing but mv by qb. What is mv? Magnitude of momentum. And for a particle, momentum is correlated with kinetic energy as under root of 2 mke. And kinetic energy, when you accelerate a charged particle through potential drop delta V, can also be written as Q delta V. So you have to remember all these formulation. So radius of a charged particle doing circular motion in a transverse magnetic field, when the magnetic field is perpendicular to projection velocity, then you say radius is mv by qb. mv can be written as magnitude of momentum by qb. For a particle, momentum can be written as under root of 2m ke by qb. And if you have provided the kinetic energy by accelerating a charged particle through potential drop delta v, then in place of ke you can even write q delta v. Now, this case, if there is some angle between the velocity and magnetic field, then the charged particle doesn't do circular motion, then it goes on a helical path. Okay, this is what they have told here. They have even discussed omega. What is the angular frequency of this circular motion? So you will say radius is mv by qb, time period equals to 2 pi r by v. In place of r, you can write mv by qb divided by v, v cancel. So time period comes out to be 2 pi m by qb. Hence 2 pi by t, which is nothing but omega, can also be written as qb by m. So same thing here. Okay, 2 pi by omega, angular velocity, is nothing but qb by m. So if charged particle projected to transverse magnetic field, radius of circular motion mv by qb, and time period is 2 pi m by qb, from there we get angular velocity is qb by m. Notice that the time period of circular motion and the angular frequency with which the charged particle rotates is independent of the speed of the charged particle. So here one important thing, this result independent of initial speed of projection. Okay, then if there is a component of velocity in direction of magnetic field, it means that projected at some angle with the magnetic field, then the charged particle undergoing helical path. Now what will be the pitch of this helix? Pitch means the distance between two consecutive turns, pitch. So what they are saying, if you have got this b and this v, break down this v into component. One in direction of b, we call it v parallel. One perpendicular to field, we call it v perpendicular. Due to v perpendicular, it does circular motion, and due to v parallel, it does straight line motion. Overall result comes out to be combination of this circular and straight line, which is called the helical path. We say that pitch is nothing but v parallel, velocity in direction of magnetic field, multiplied by time taken to complete one circular motion, which is 2 pi m by qb. V parallel into 2 pi m by qb. This is the pitch. This formula is given. See once more, baby. Pitch is nothing but v parallel into time period of circular motion. So v parallel into 2 pi m by qb. Simple questions will come based on this. Then we have got something called Biot-Savart's law. See here, dB equals to mu naught by 4 pi I dl cross r by r cube. dB equals to mu naught by 4 pi I dl cross r by r cube. The value of mu naught by 4 pi is 10 raised to the power of minus 7. The value of mu naught by 4 pi is 10 raised to the power of minus 7. This formula tells us what is the strength of magnetic field. So if you have this current carrying conductor and you wish to write the magnetic field due to an infinitely small element of this conductor at a point in space, then you write the infinitely small magnetic field created by this infinitely small current element is mu naught by 4 pi, which is 10 raised to the power of minus 7, into I dl cross r by r cube. Notice that again we get magnetic field from cross product of dl and b. Remember that the direction of dl always have to be taken in the direction of current. Direction of dl has to be taken in the direction of current. Magnetic field on the axis of a circular current carrying loop. Beto, remember this formula given in NCERT. Magnetic field at a point on the axis is mu naught I r square upon 2 times of r square plus x square raised to the power of 3 by 2. So if you have a current carrying loop carrying a current I, and we wish to write magnetic field at a point here whose distance from the center of this loop is x and whose radius is r, we write that the magnetic field is mu naught I r square by 2 times of r square plus x square raised to the power of 3 by 2. Use your photographic memory, mug it up right now. Magnetic field at a point on the axis is mu naught I r square by 2 times of r square plus x square raised to the power of 3 by 2. Mu naught I r square upon 2 times of r square plus x square raised to the power of 3 by 2. Mu naught I r square upon 2 times of r square plus x square raised to the power of 3 by 2. If you substitute x0, then here you will get in denominator r square raised to the power of 3 by 2, which will be r cube. R cube in denominator, r square in numerator. So in that you will be left with an r in denominator. So magnetic field at the center of a circular current carrying loop. So if there is a current carrying loop carrying a current I, then the magnetic field at its center is nothing but mu naught I by 2r. Mu naught I by 2r. Okay. So these two formula you have to remember. Once more, look at them. Magnetic field at a point on the axis of a current carrying loop, mu naught I, radius of the loop whole square, by 2 times of r square plus x square raised to the power of 3 by 2. And at center, mu naught I by 2r. Then we have got something called Ampere circuital law. Ampere circuital law tells us that closed integral of B dot dl equals to mu naught times current inside. Do realize Gauss law works on a closed surface. Ampere circuital law works on a closed loop. Gauss law works on a closed surface. Ampere circuital law works on a closed loop. So closed integral of B dot dl equals to mu naught times current inside. Now here we have to assign a sign to the current. So let's say this is our Amperian loop. Okay? Collection of all the small length. It's a loop, not a surface. Now, if you are going in this Amperian loop clockwise, then use the right hand thumb rule to identify which current has to be marked as positive and which current has to be marked as negative. If you go in this Amperian loop clockwise, then inward current will be taken as positive and outward current will be taken as negative. So within this Amperian loop, let's say 2 wires are passing, one carrying inward current I1, one carrying outward current I2. So if you go in the Amperian loop clockwise, then I1 will be positive, I2 will be negative. And if you go in an Amperian loop anti-clockwise, then outward current, the direction in which your thumb points, outward current will be positive while inward current will be negative. Okay. Using Ampere circuital law, we can find that due to an infinite wire carrying a current I, the magnetic field at distance r from it is equals to mu naught I by 2 pi r. This result implies that the field at every point on the circle of radius r with the wire along the axis is same in magnitude. In other words, magnetic field possesses what is called cylindrical symmetry. So if you have a wire, then at all the points at same distance r, the magnitude of magnetic field is same. Field is a vector quantity, so direction keeps on changing tangentially, magnitude is same. The field direction at any point on this circle is tangential to it. Third, another interesting point to note is that even though the wire is infinite, the field due to it is a non-zero distance is not infinite. Wire is infinitely long, but at a finite distance from it, you get a finite magnitude of magnetic field, not infinitely large magnetic field. Okay, Bittu. Now, what they are saying, there exists a simple rule to determine the direction of magnetic field due to a long wire. This rule, called the right hand thumb rule, which I have said at the very beginning, align the thumb of right hand in the direction of current. The way your fingers curl around the thumb, the same way magnetic field lines curl around this current carrying wire. Now then there is some question. But if rather than having a wire, you have current uniformly distributed over the cross section. This have came in NEET already. Then as you move from axis to surface, magnetic field strength increases linearly, and for outside point, the magnetic field is proportional to 1 by R. So if you have this solid rod carrying a current I uniformly distributed over its cross section, and let's say it has a radius R, then at a distance small r from axis, magnetic field is given by magnetic field on surface, which is mu naught I by 2 pi r into chinna r by pedda r. This is for inside point. Magnetic field is directly proportional to r. For outside point, simply put the entire wire on the axis. So for outside point, magnetic field is simply equals to mu naught I by 2 pi r. So as you go from axis to surface, magnetic field strength increases linearly, and for outside point proportional to 1 by r. Let's move on, bachcho. Then we have got solenoid. Important result here as well will come. The magnetic field due to a solenoid inside it is nearly uniform, and this magnetic field inside solenoid is nothing but mu naught Ni. Beta, mu naught by 4 pi is 10 raised to the power of minus 7. Value of mu naught is 4 pi into 10 raised to the power of minus 7. This term n here is nothing but number of turns per unit length. Number of turns per unit length. So if we have this solenoid in which the number of turns is capital N and the length of solenoid is L, then we say the number of turns per unit length is total number of turns upon total length of the solenoid. So we do mug up the formula fast. Magnetic field inside a solenoid is nearly uniform. How much? Mu naught Ni. Mu naught Ni. Mu naught Ni. Mu naught is 4 pi into 10 raised to the power of minus 7. N is the number of turns per unit length. I is the current flowing through the solenoid. Again, important heading. Force between two parallel current carrying wires. So if you have got two parallel current carrying wire, first of all focus on this. If two parallel current carrying wire carry current in same direction, they attract each other due to magnetic force. If two parallel current carrying wire carry current in opposite direction, then they repel each other due to magnetic force. One more time. If two parallel current carrying wire carry current in same direction, they attract each other due to magnetic force. If they carry current in opposite direction, they repel each other due to magnetic force. Now how much is the force? The force acting per unit length is given by mu naught I1 I2 by 2 pi d. So if let's say there are two current carrying wire having current I1 and I2, and the separation between them is d, the first wire carrying current I1 produces a magnetic field at position of I2. The magnetic field created by 1 at position of 2 is nothing but mu naught I1 by 2 pi d. And the force experienced by a length L of the second wire is current in the second wire. It's actually I into L cross B. But since here L and B are perpendicular, the angle between L and B is 90 degree and sine 90 is 1. So we are not writing it. So the force experienced by second wire is current in the second wire into length of second wire into the perpendicular magnetic field created by first wire at position of second wire. Okay. Hence you get force equals to mu naught I1 I2 L by 2 pi d. You have to remember all these formula. Basic questions come. Mu naught I1 I2 by 2 pi d. What is this? Force acting per unit length of one of the wire. Mu naught I1 I2 by 2 pi d. Mu naught I1 I2 by 2 pi d. This is the force acting per unit length on one of the wire. Now betu, same thing, force acting per unit length, mu naught I1 I2 by 2 by d. Important result. Torque on a current loop. A current carrying loop is nothing but a magnetic dipole. A current carrying loop is nothing but a magnetic dipole. Now betu focus. If a current carrying loop carries current clockwise, then at a point inside it, the direction of magnetic field can be again found using right hand thumb rule. So if the current is clockwise, we say this pole, this phase on which we are looking, this is south pole. And if the current in the loop is anti-clockwise, then we say the phase we are looking on, that is the north pole. So remember first thing, a current carrying loop is a magnetic dipole. If it's a magnetic dipole, it needs to have north pole and south pole. If the current is clockwise, the phase you are looking at, that is south pole. And if the current is anti-clockwise, then the phase you are looking at is north pole. Now look at the fingertip. I am moving it clockwise, anti-clockwise, that doesn't matter sometimes. But what I am saying is, if as seen by me, this fingertip goes anti-clockwise, then as seen by you, it will be clockwise, right? So as seen by me, as the current goes anti-clockwise, I will say the pole I am looking in this loop is north, and you will say the pole you are looking on the same loop is south. So a current carrying loop acts like a magnetic dipole. One of the person will see north, the person on opposite side will see south. Now beta, bhaad mein ja, all this useless stuff, just focus on the final result. Just like for electric dipole, torque acting on electric dipole is P cross E. In the same way, the torque acting on a magnetic dipole is M cross B. What is M? This P is called electric dipole moment. This M is called magnetic moment. Magnetic moment. So torque on dipole in uniform electric field is P cross E. Torque on magnetic dipole in uniform magnetic field is M cross B. Now beta, what is M? M is current times area vector. So if you have got this loop carrying current clockwise, you will say area vector is into the plane. If the same loop carries current anti-clockwise, you will say out of the plane. One important thing here, remember betu, magnetic moment also depends number of turn in the loop. So if you have got n turns in the loop, then the magnetic moment is NIA. Number of turns in the loop times current in the loop times the area vector. The direction of area vector is decided using the right hand thumb rule. The direction of area vector is decided using the right hand thumb rule. Curl the fingers of right hand in the sense of current. The direction in which your thumb point is the direction of magnetic moment. One more time saying, if you have this loop, let's say carrying current clockwise, curl the finger of right hand in the sense of current. The direction of thumb gives you the direction of area vector. So this is important thing. So magnetic moment associated with a current carrying loop is NIA, N is number of turn, I is current, A is the area vector. And the torque acting in the uniform magnetic field is given by M cross B. M cross B. Chalo bachcho, let's move on. Now, circular current loop as a magnetic dipole. We already know that magnetic field due to a circular current carrying loop at a point its axis is mu naught I r square by 2 times of r square plus x square raised to the power of 3 by 2. Now they are trying to compare this with the magnetic dipole. They will say I into pi r square, I current into area will be magnetic moment, right? And they will say for a large distance, for x greater than r, if x is greater than r, you can neglect this r square. So what you get is mu naught I r square by 2 times of x square raised to the power of 3 by 2, which is x cube. Bachche multiply with a pi, divide with a pi. This I pi r square can be written as magnetic moment. And now multiply with a 2, divide with a 2. So what you get is 2 mu naught by 4 pi into magnetic moment by x cube. And we already know, due to an electric dipole at a point on its axis, the electric field is 2 kp by r cube. I call this mu naught by 4 pi as c, just to compare. There k is 1 by 4 pi epsilon naught, mu naught by 4 pi is c. So we say if you have a magnetic dipole of dipole moment m, then at a point on the axis, the magnetic field comes out to be 2cm by r cube. What is c, bacho? Mu naught by 4 pi. Just like here, k is 1 by 4 pi epsilon naught. So that's the comparison they have done here. Okay. Electric field at a point on axis 2 kp by r cube. Magnetic field at a point on the axis of magnetic dipole, that will be 2 cm by x cube. This must be Betu result of equatorial point. Hai na? This is equatorial point and this is for axial point. Equatorial point, if you have a bar magnet of magnetic moment m, then at a distance r here will be 2 cm by r cube, and at an equatorial point, same distance from both the poles, direction of magnetic field will be opposite, and that will be only cm by r cube. C is mu naught by 4 pi, whose value is 10 raised to the power of -7. Then we have called moving coil galvanometer. Dekh betu. All you have to remember in moving coil galvanometer is that when you drive the current flows through a coil. Inside the galvanometer, there is a magnetic field. Magnetic field applies a torque. Magnetic field cross B, magnetic moment cross B. Magnetic moment is NIA into magnetic field. This is the torque due to magnetic field. And there is a spring underneath it. As soon as magnetic field applies torque, the coil tries to turn. The spring provides a restoring torque. And that restoring torque is nothing but c theta. So we get, or here they have written it as k theta. So they are saying the angle turn deflection in the galvanometer per unit current is nothing but NAB by K. This quantity theta by I is called current sensitivity of a galvanometer. This is called current sensitivity of a galvanometer. Now, they are saying a convenient way for the manufacturer to increase the sensitivity is to increase the number of turns in the coil N. We choose galvanometers having sensitivity of the value required by our experiment. Some experiment requires more sensitivity, some experiment requires less sensitivity. Then they have said further, current sensitivity theta by I equals to NAB by K. If I divide both the side with the resistance of the coil, IR becomes potential drop. Now we have a new term which is called voltage sensitivity. The deflection per unit applied voltage. Voltage sensitivity. This is NAB by K divided by an extra term of R. Do realize you can increase the current sensitivity by increasing the number of turns, but you can't increase voltage sensitivity by increasing the number of turns. They have explained here. If the number of turns is doubled, then the resistance also doubles. So if the number of turns you double, then you are using double the length of wire in the coil, then the resistance also double, voltage sensitivity remains the same. So current sensitivity of a galvanometer can be increased by increasing the number of turns, but voltage sensitivity can't be increased by increasing the number of turns. Let's move on. This brings us to the next chapter, which is magnetism and matter. First, Earth behaves as a magnet with a magnetic field pointing approximately from the geographic south to the geographic north. Earth creates a magnetic field of its own, direction from south to north. When a bar magnet is freely suspended, it points in the north-south direction. The tip which points to the geographic north is called north pole of bar magnet, and the tip which points towards geographic south is called south pole of bar magnet. Then there is a repulsive force when north poles are brought together, and there is a repulsive force when two south poles are brought together, while north and south will attract each other. Next, we cannot isolate the north or south pole of a magnet. If a bar magnet is broken into two halves, we get two similar bar magnet with somewhat weakened property, not strong enough. Unlike charges, isolated north and south pole do not exist. So north and south pole always exist in pair. If we take a bar magnet which has north here, south here, and we break it into two parts, we again get two smaller bar magnet with north, south, like this. Next, it is possible to make magnets out of iron and its alloy. You can magnetize iron, its alloy. The most commonly used are FeCO(Ni), FeCO(Ni). They are most commonly used for making permanent magnet. Then they have talked about bar magnet. In this chapter, there are less formulas. This is more of a theoretical chapter. Now, beta, same thing. If you have a magnetic dipole of magnetic moment M at a point on its axis, the magnetic field is 2C. C is mu naught by 4 pi M. M is the magnetic moment here by R cube. This M is not pole strength, baby. This is magnetic moment of the bar magnet. Same formula. Magnetic dipole in uniform magnetic field. In electric, torque is P cross E. Here torque is M cross B. This M is magnetic moment. Potential energy. There we know potential energy is minus P dot E. Here potential energy is minus M dot B. M is magnetic moment, B is magnetic field. When you are doing dot product, write the magnitude of first vector into magnitude of second vector into cos of the angle between them. The electrostatic analog, just like in electrostatic you have electric field and magnetism you have magnetic field. In electrostatic you have got electric dipole moment. In magnetism you have magnetic moment. In electrostatic you have 1 by 4 pi epsilon naught, which has a beautiful value 9 into 10 raised to the power of 9, easy to remember. In magnetism you have got mu naught by 4 pi, which is again a beautiful value, easy to remember, 10 raised to the power of minus 7. Now see how many times they have written the same formula. Magnetic field at equatorial point, Cm by r cube, but with a minus sign because it's opposite direction. Magnetic field on axis 2Cm by r cube. Now, magnetism and Gauss law. Electric field line sometimes forms a closed loop and sometimes doesn't form a closed loop. But magnetic field lines always form a closed loop. The net magnetic flux linked with a closed loop is always zero. The net magnetic flux linked with a closed loop is always zero. Okay, because if the magnetic field line will enter, they will also exit. While entering, the flux linked will be negative, while exiting it will be positive. The net magnetic flux linked with a closed loop is always zero. Now bachcho, magnetization and magnetic intensity. What in classes we use the word I. We say I, which is magnetization, is the magnetic moment developed per unit volume. You take a crystal, keep it in external magnetic field, dipoles align. This alignment of dipole gives it the magnetic moment. The magnetic moment developed per unit volume is the intensity of magnetization. Next formula. We will say intensity of magnetization is susceptibility times magnetizing field intensity. Now what is this magnetizing field intensity? To magnetize a crystal, we have to keep it in external magnetic field. This external magnetic field divided by mu naught is the magnetizing field intensity. The stronger the external field we deploy, the better the alignment happens, and we say stronger is the magnetizing field intensity, the field intensity which is trying to magnetize the material. And this proportionality constant is called susceptibility. Now, betu, one more important thing here. The permeability of a medium is permeability of free space times relative permeability. And relative permeability is nothing but 1 plus susceptibility. So if susceptibility is 5, relative permeability is 6. Susceptibility is 10, relative permeability is 11, and so on. Magnetic property of material. Beta, this now you have to remember, it can be asked. So I am focusing on it. We divide magnetic material into 3 things: diamagnetic, paramagnetic, ferromagnetic. Diamagnetic material tries to move from stronger magnetic field region to weaker magnetic field region. Paramagnetic material tries to move from weaker magnetic field region to stronger magnetic field region. Paramagnetic wants to be in region of strong magnetic field. Ferromagnetism is nothing but an extreme case of paramagnetism. For diamagnetic material, susceptibility lies between 0 and -1. Susceptibility is negative. We have just learned a formula betu I equals to psi h. Right? For diamagnetic material, susceptibility is negative. So if you deploy a magnetic field towards right, it develops a magnetic moment towards left. Okay? Then so next thing, you add 1 here. Add 1 here, you get the next result, because we already know mu r equals to 1 plus psi. So for diamagnetic material, susceptibility lies between 0 and -1. Hence, mu r lies between 1 and 0. Add 1 to both the sides. For paramagnetic material, susceptibility lies between 0 and E. This E means some small number. Small number, hai na? It can't be a big number. Susceptibility is big number for what? Ferromagnetic material. Chalo bachcho. Then they have explained what is diamagnetism, what is magnetism, what is ferromagnetism. Now we will move on to the next chapter, which is our EMI, electromagnetic induction. So first of all, we have to talk about certain experiment. Experiment number 1. When a bar magnet is pushed toward a coil, the pointer of the galvanometer G deflect. So these observations were made. You take a coil, connect with a galvanometer. Notice that in this circuit there is no cell. And if you move a bar magnet, then there is a deflection in the coil. The faster you move the bar magnet, the more is the deflection in the coil. And third, when you flip the polarity and then you move, then the direction of deflection changes. For example, when you were moving north towards coil, if the deflection was towards right, then when you move south towards the coil, then the deflection is towards left. So what Faraday made the observation, first observation was that there is a coil connected to a galvanometer. There is no battery. Nobody to drive current into it. Then he took a bar magnet. When you push the north of the bar magnet, there is a deflection. The faster you move, the more is the deflection. You stop moving the bar magnet, the current in the galvanometer drops to 0. You change the direction of bar magnet and then move it, then the direction of current also changes. So these are the observations which are written here. One more thing which was observed. Now let's say you don't have a bar magnet. You have first coil connected to a galvanometer without battery, and then you have second coil connected to a battery. So in this second coil, the battery will drive current. When you move this second coil towards the first coil, same behavior was observed as for bar magnet. For example, till the time you are moving the second coil, there is a current in the first coil. You stop moving the second coil, there is no current in first coil. The faster you move the second coil, the more is the deflection in the galvanometer connected to first coil. You change the direction of motion, polarity of the second coil, the deflection there changes. Same observation were made. Now, here we define something called magnetic flux. Just like electric flux is integral E dot dA, magnetic flux is integral B dot dA. So addition of all the small magnetic flux linked with every single small area gives you the total flux linked with the area. The unit of magnetic flux is Weber, or which is also same as Tesla, unit of magnetic field into meter square. Then we have got Faraday's law. Faraday's law says that the EMF developed is minus d phi b by dt. EMF equals to minus d phi b by dt. Do realize here the minus sign tells us one thing, that due to the change in magnetic flux, the EMF induced will try to kill out the reason why the flux is changing. So if the flux is increasing in a particular direction, the EMF will try to create a current which will oppose the change in this magnetic flux. This is what the minus sign represent. E equals to minus d phi by dt. Now, Lenz law and conservation of energy. Earlier in old NCERT, the same heading was Lenz law as an outcome of conservation of energy. Okay, so beta, in Lenz law also energy is conserved. What they are trying to say, when you move the north pole of a bar magnet towards a coil, the north pole gets repelled. When you move the bar magnet towards the coil, a current is driven in the coil. This current has some energy associated with it. It will dissipate a power I square R in a time t. The total energy released will be I square RT. So question is that how do you get current in a loop? By doing work. To move the bar magnet towards the coil, you have to apply force on the bar magnet. So you are doing some work, and that work is the one creating this current. Now, beto, this question. Figure shows planar loops of different shape moving out or into a magnetic field region which is directed normal to the plane of the loop away from the reader. Determine the direction of induced current in the loop using Lenz law. So first, this triangular loop is going out. When this triangular loop is going out, the number of magnetic field lines going inward, passing through it inward, will decrease. Lenz law tells us that every time there is a change in magnetic flux, an EMF will be produced which try to oppose the change in the magnetic flux. So as this loop will try to move out, the flux will decrease because the number of magnetic field lines going in are decreasing. So as to oppose the change, an induced current will be developed which will try to produce inward magnetic field. To produce inward magnetic field in this loop, you need to have clockwise current. Similarly, here this is entering. So the number of magnetic field lines passing inward are increasing. So as to oppose the change, the current in the loop tries to produce outward magnetic field, for that anti-clockwise. Here it is going out. Since this loop is going out, the number of magnetic field lines passing and going in will decrease. So magnetic flux due to the field in will decrease. Why is the flux decreasing? Because the number of field lines going in are decreasing. So as to oppose the change, this loop will try to create inward magnetic field. And for that, there has to be a clockwise current. This question can come this year, right? But be cautious in these type of question. They don't mention which side is front, which side is back. Right? So this side is back and the capacitor side is on the front. Moving on. Motional electromotive force. You don't have to do PhD on it. Just remember that, beto. The motional EMF developed is BLV. So if the length of the rod, velocity of the rod and magnetic field all are mutually perpendicular, length of the rod, velocity of the rod and magnetic field all are mutually perpendicular, then the EMF developed across it is BLV. Betu, this is important. If you have a rod of length L, which is rotating with an angular velocity omega at a place where the magnetic field is B, then across the ends an EMF will be developed, and this rotational motional EMF will be, you can again think using BLV, magnetic field into L. Which velocity to take? This end's velocity is 0, omega r. This is hinge point. This end's velocity is omega L. So take the average. So 0 plus omega L by 2. So that's why the motional EMF comes out to be B omega L square by 2. So if you have a rod of length L going with a velocity V at a place where magnetic field is B, motional EMF is BLV. If you have a rod having length L going with an angular velocity omega at a place where magnetic field is B, then the motional EMF will be B omega L square by 2. The common error which happens here is that out of our habit of centripetal acceleration omega square L, omega square R, omega square R, we end up doing sometimes B omega square L by 2. Be cautious. Start thinking from scratch. Motional EMF is BLV. Here the velocity is changing. This end velocity is 0. This end velocity is omega L. So we get BL into 0 plus omega L by 2. Hence B omega L square by 2. Chalo bachcho. Now we are going to talk something called inductance. The property of a substance by which it opposes the change in current flowing through it is called inductance. The property of a substance by the virtue of which it opposes the change in current flowing through it is called inductance. Now there are two types of inductance: mutual inductance, and then we have got something called self-inductance. One is mutual inductance, one is self-inductance. Let's say there is a coil. If you change the current flowing through this coil, then the magnetic field linked with this area, passing through this area, will change. So if current changes, then magnetic field will change. If magnetic field will change, then flux will change. When the flux will change, EMF will be induced. EMF induced tries to oppose the change in flux. To oppose the change in flux, you have to oppose the change in magnetic field. To oppose the change in magnetic field, you have to oppose the change in current. When an EMF is induced in a coil due to the change in current in that coil, that is called self-inductance. When an EMF is induced in a coil due to the change in current in same coil, that is called self-inductance. Then sir, what is mutual inductance? Let's say there are two coils. This is coil 1 and then there is this coil 2. Let's say we drive some current in the coil 1. When we drive some current in the coil 1, this coil also produces some magnetic field at the position of coil 2. When we change the current in the coil 1, the magnetic field at the position of coil 2 will change. Due to the change in the current in the first coil, an EMF is induced in the second coil. This is called mutual inductance. Now, remember one thing. In self-inductance, the EMF developed due to the change in current in same coil is proportional to rate of change of current with respect to time. You change the current fast, the magnetic field will change fast, the flux will change fast, and more EMF will be induced. Then we add up a proportionality constant, which is called the inductance, and we write E equals to L di by dt, a minus sign, just to show that the EMF induced is such that it opposes the change in current. One very important relationship going to come from here. We already know that from Faraday's law, E equals to minus d phi by dt. So minus d phi by dt is equals to minus L di by dt. Dt cancel, minus minus cancel. So we say that the infinitely small change in flux linked with a coil equals to self-inductance of the coil times infinitely small change in current. And on integrating both the sides, we say flux linked with a coil equals to self-inductance of the coil times current flowing through the coil. Phi equals to Li. Phi equals to Li. Okay? The flux linked with a coil equals to self-inductance of the coil times the current flowing through the coil. Now, we will look at the same formulas one by one. So first, let's go back to mutual inductance. Here also some formulas I have skipped. Let's talk about it. Now here. We say that the mutual inductance of coil 2 due to coil 1 is same as mutual inductance of coil 1 due to coil 2, which is M. Now, if you have this first coil and this, you change some current, let's say current flowing is I1, you change the current I1 and EMF will be induced in the second coil. We say that the EMF induced in the second coil is directly proportional to the rate of change of current in the first coil with respect to time. And then we add a proportionality constant. This time, what we add is called mutual inductance di1 by dt. Again, you can write EMF developed in second coil as minus d phi 2 by dt equals to minus m times di1 by dt. Dt cancel, minus minus cancel. We say that integrating both the sides. Flux linked with second coil equals to mutual inductance time current in the first coil. Flux linked with second coil equals to mutual inductance time current in the first coil. So they might ask you a very stupid question that there is coil 1, there is coil 2. When we drive a current of 5 ampere in coil 1, due to the current in coil 1, the flux linked with coil 2 is 20 Weber. Then what is the mutual inductance? So mutual inductance will be simply phi 2 by I1. That will be 20 by 5 and 20 by 5 is 4. Okay. Now let's move on. Here, there is a formula for a mutual inductance of pair of solenoid. Let's do it really fast and understand it. How did they get it? So Betu, here they have shown us two long coaxial solenoid of same length L. Now, if you drive some current in this outer one, let's say I2, and simply find what is the flux linked with this inner one, okay, then you will say flux linked with inner equals to mutual inductance times current in outer. If in the outer one there is a current I2, then the magnetic field created here will be nothing but mu naught N2 I2. This is the magnetic field. Now the area of one turn of this inner one will be pi r1 square, radius of this, pi r1 square. So the flux linked with one turn of inner equals to magnetic field mu naught N2 into area of one turn, which is pi r2 square. Flux linked with one turn. How much turn this inner coil has? The inner coil has total number of turns per unit length into length of this L. Now this is better total flux linked with inner. This is magnetic field. This is area of one turn. This is the number of turn. Flux linked with inner equals to mutual inductance times current with outer. So leaving apart this I2, whatever you have on board, that is the mutual inductance. So these formula are not tough. If you break them down step by step, this is the field, multiply with area, this is the flux, then this is the number of turn. Moving on, bachcho. Self-inductance. Okay. Energy stored inside an inductor, half Li square. Easy to bug up, easy to remember. Remember just one thing. Between the plates of capacitor, energy is stored in the form of electric field. Inside an inductor, energy is stored in the form of magnetic field. Energy stored inside an inductor of inductance L, when a current I flows through it, is half L I square. Inside inductor, energy is stored in the form of magnetic field. Now we have got AC generator. In AC generator, again, most important thing is this: peak EMF or the amplitude of EMF. In AC generator, peak EMF maximum is NBA omega. Peak EMF generated in an AC generator is NBA omega. What is N? Number of turns in the coil which is being rotated. What is B? Magnetic field. What is A? Area of the coil which is being rotated, and omega is the angular velocity with which you are turning the coil. NBA omega. The maximum EMF generated in an AC generator is NBA omega. Next, this brings us to the last chapter which we have to do. Beto, this question came in NEET 2024. This question came in NEET 2024 and many kids did wrong. That's why doing NCERT becomes important. So this brings us to the last one, AC. So if you put an AC source across a resistor, then the current flowing is nothing but peak value of voltage divided by resistor sine omega t. For a pure resistive circuit, the potential and the current have same phase. So potential is Vm sine omega t. See, current also same. Vm by R, maximum voltage divided by R sine omega t. In a pure resistive circuit, current and potential are in same phase. This is even clear from this graph. When potential 0, current 0. When potential maximum, current maximum. When potential 0, current 0. When potential negative maximum, current negative maximum, and so on. So in a pure resistive circuit, when you connect AC to a resistor, then current and potential both are exactly in same phase. Now power. Power dissipated is an AC circuit, has the same formula, mota mati, more or less, as in DC. Here also you can say that the power dissipated is I square R. But which I do you have to take? We take I RMS. For sinusoidal function, I RMS is peak current by root 2. For sinusoidal function, RMS value is peak current by root 2. Sir, what is sinusoidal function? Sine function or cos function? So if I say that current is 4 sine omega t, then the RMS value of current will be 4 by root 2, which is 2 root 2. Important thing here, focus bachcho. A special value of current is defined and used. It is called root mean square or effective current and is denoted by IRMS. In an AC, current continuously change. IRMS is that one constant current that can be assumed to be flowing so that the system dissipates the same power as it actually does. IRMS is that one constant current that can be assumed to be flowing so that system dissipates the same power as it actually does. Okay? So then they have found the value of IRMS. IRMS is nothing but peak divided by root 2. Okay, I maximum by root 2. Similarly, but to VRMS is V maximum by root 2. One constant doubt which I get from kids, sir, how to know in the question that this is RMS value or peak value? By simple rule. If in question amplitude, peak, maximum, or equation like 20 sine omega t plus phi, these things are not given and nothing is said, it's always RMS. For example, if they say a 50 volt AC supply is attached, this 50 volt is RMS. A 4 ampere AC current is flowing, this 4 ampere is RMS. If they say the amplitude of current is 4, then peak. The peak value of current is 4, then means maximum value. Maximum is 4. Or if they write something like this, 20 sin omega t. Now this 20 is amplitude. So if in AC nothing is mentioned, it's always RMS. If it's not RMS, they will use one of these things. Okay. Now, a light bulb is rated this, for this much supply. Find the resistance of bulb, peak voltage of source, and RMS current through the bulb. So let's do this question fast. First of all, in this question, this 20 given, this is equal to RMS value. So when they ask the peak voltage of source, 220 is peak potential by root 2. So peak potential has to be 220 into root 2. B part done. What is the resistance of bulb? We say that the power dissipated equals to I RMS whole square into R. Now sir, how to get I RMS? Very easy. Power dissipated is for a resistor only I am saying. V RMS into I RMS. V RMS you know 220. I RMS will be 100 by 220. So you write 100 equals to 100 by 220 whole square into R. From here you can find out the resistance. And then the third part, the RMS current in the bulb, that we have found already, 100 by 220. Now, representation of AC current and voltage by rotating vector, which is called phasor method. Now we are going to talk about inductor. When you connect an inductor to an AC source, the peak current equals to peak potential drop divided by XL. So what is XL? XL is omega L. So in a pure resistive circuit, peak current is peak potential drop by resistance. In pure inductive circuit, when you connect only an inductor, peak current equals to peak potential drop divided by XL. What is XL? XL is omega into L. XL is omega into L. In a pure resistive circuit, the potential drop applied across resistance and the current flowing through the resistor are in same phase. But in pure inductive circuit, current lags potential by pi by 2. In which one beta? In pure inductive circuit. So let's say I give you following data. Let's say XL is 4 ohm. Okay. This supply line potential is 20 sin omega t. Tell me, how will you write current in this inductor? Sir, what is this? This is supply line potential. Okay. So देखो sir. Peak current will be peak potential drop divided by XL. ठीक है. So peak current will be 5. In an inductor, the current lags behind the phase of potential by pi by 2. So if the phase of potential is omega t, then the phase of current will be omega t minus pi by 2. So what do you have to remember in pure inductive circuit? 3 things. First, peak current equals to peak potential drop by XL. Yes, sir. XL is omega L. Yes. In a pure inductive circuit, current lags potential by a phase of pi by 2. Now, moving on to the next one. Our pure capacitive circuit. Now see here. Beto, figure, graph. This is the I and V. This is the I and V for pure inductive circuit. Notice that when potential is 0, current is negative. When potential became positive, maximum current became 0. When the potential started decreasing and became 0, then current became maximum. So current lags behind potential by a phase of pi by 2 in pure inductive. Now let's move on to pure capacitive. Just like in pure inductive, in pure capacitive, peak current equals to peak potential drop by Xc. Xc is called capacitive reactance. Xc is 1 by omega c. Xc is 1 by omega c. In a capacitor, in inductor, who lags? In inductor, current lags. In capacitor, potential lags current by pi by 2, or current leads potential. Both are same thing. Current leads potential by pi by 2. So in pure resistor, peak current is peak potential drop divided by R. In pure resistor, current and potential drop are in same phase. In pure inductor, peak current is peak potential drop by XL. XL is nothing but omega L. In pure inductor, current lags behind potential by pi by 2, or potential leads current by pi by 2. In pure capacitor, peak current is peak potential drop by Xc. Xc is 1 by omega c. In a pure capacitive circuit, potential leads current. Sorry. In pure capacitive, current leads potential by a phase of pi by 2, or potential lags behind current by a phase of pi by 2. So let's do one stupid question here also. Let's say this is your pure capacitive circuit. This time you have connected a capacitor. And let's say Xc is 4 ohm. This time your supply EMF is 20 sine omega t. Beta, this is EMF. In the capacitor, current has to lead by a phase of pi by 2. So if I ask you what is the current at any time t, so you'll say, dekho sir, peak current will be peak potential drop by capacitive reactance, that comes out to be 5. This time current has to lead by a phase of pi by 2. So 5 sine omega t plus pi by 2. Okay, so easy. Now, look here, this figure. This is V, this is I. This time current leads. When the potential is 0, current is maximum. When potential becomes maximum, current has already become 0. So current is ahead by a cycle of pi by 2 compared to the potential. Moving on. AC voltage supplied to LCR circuit. There are some equation which you are not going to get into. Here now you have to remember something called impedance. Two things, impedance. The impedance of a circuit is under root of resistance of the circuit square plus reactance of the circuit square. Xc minus XL or XL minus Xc, magnitude of that, that's called reactance of the circuit. So if you have R, if you have XL, if you have Xc, this direction becomes R, and in this direction we get XL minus Xc, or if you think Xc to be bigger than XL, then you get in this direction Xc minus XL. And this is under root of R square plus Xc minus XL whole square. Do realize here Xc minus XL, XL minus Xc doesn't matter, because anyways you are squaring it. Who is more, who is less, doesn't matter. But in a circuit, if XL is more than Xc, then inductor is dominant. Inductor ensures that current lag. Capacitor ensures that current leads. So if in a circuit XL is more than Xc, then current lags, but not by 90 degrees, because circuit has R and C as well. And if Xc is more than XL, then current leads potential by some angle. Okay, keep this thing in mind. When current will neither lead potential nor lag potential. So in an LCR circuit, current will neither lead potential nor lag potential when XL will be equals to Xc. XL is omega L, Xc is 1 by omega C. So when omega square equals to 1 by LC, then it neither leads nor lag. Or when omega is 1 by root LC, then it neither leads or lag. Okay. This condition is called resonance condition. When XL becomes equals to XC, this happens when the angular frequency of the source is 1 by root LC. And when they become equal, important, very important, when the resonance frequency means XL and XC cancel out each other. This whole part becomes bache 0. So under resonance condition, omega is 1 by root LC, impedance of the circuit is R, current and potential are in same phase. So these three things we have to remember. Okay, bacho? Chalo, let's move on. Resonance condition we have just learned. Resonance frequency is 1 by root LC. Impedance is R. It is important to note that resonance phenomena is exhibited by a circuit only if both L and C are present in the circuit. Then only they will cancel. Only then do the voltage across L and C cancel each other, both being out of phase. And the current amplitude is V maximum by R. The maximum value of voltage drop applied divided by R. And the total source voltage appear across the resistor under resonance condition when omega is 1 by root LC. This means that we cannot have resonance in RL or RC circuit. Chalo, let's move on. Power in an AC circuit, the power factor. Beto, we don't do everything, we will focus right where it matters. Hai na? So, the value of power comes out to be Beto. This is VRMS, this is IRMS cos phi. So, power is VRMS, IRMS cos phi. Power is VRMS, IRMS cos phi. Here this quantity cos phi is called power factor. It's called power factor. What is phi? Phi is the phase difference between current and potential. What is phi? Phi is the phase difference between current and potential. So, power in an AC circuit is VRMS, IRMS cos phi. Phi is the phase difference between current and potential. Let's read the 3 point important. Case 1. In a purely resistive circuit, if the circuit contains only resistance, it is called resistive circuit. In that case, since the current and potential are in same phase, phi is 0 and hence cos phi is 1. In this case, phi is 0 and hence cos phi is 1. This is the maximum power dissipation. So, power is VRMS, IRMS cos phi. Power dissipation will be maximum when cos phi will be maximum. Cos phi is maximum 1 when phase difference between current and potential is 0. Case 2. Purely inductive or capacitive circuit. If the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current will be 90 degree, pi by 2. Therefore, cos 90 is 0 and no power is dissipated even though the current is flowing in the circuit. This current is sometimes referred to as wattless current. So what is the meaning of wattless current? A current is flowing, but still there is no power dissipation due to it. That's called wattless current. Betu, 1 second come. VRMS, IRMS, cos phi. This is what? Power dissipated. Here we use phasor diagram. So we say, let's say this is IRMS, this is VRMS, and let's say there is an angle phi between them. I know that current is not a vector quantity, but phasor is a trick to treat these sinusoidal function as vectors. So we can think of this IRMS to be made up of two components. One here, IRMS cos phi, and one here, IRMS sin phi. We say that power loss happens due to this IRMS cos phi, and no power loss happens due to this IRMS sin phi. So what is the wattless current? Wattless current is IRMS sin phi. What is the wattless current? I RMS sin phi. So let's quickly do a question and tell me what is the power dissipated and what is the wattless current in this case. If they give you potential is 20 sin omega t, Anji, and current in the line is 10 sin omega t plus pi by 3. And they ask you what is the power dissipated? Power dissipated. So you say, देखो sir, power dissipated. VRMS. VRMS how much? Not 20. 20 is peak. VRMS 20 by root 2, which is 10 root 2. IRMS. Peak is 10 current. RMS value will be 5 root 2. VRMS, IRMS. Cos phi. Cos of pi by 3. Pi by 3 is 60. Cos 60 is half. So this root 2 multiply and become a 2. This half cancel. Power loss comes out to be 50. In the same question, they might ask you what is the wattless current. So you will say, Dekh bhai, wattless current is I RMS sin phi. The value of I RMS will be peak by root 2. So 10 by root 2, which is 5 root 2. What is the value of sin phi? Phi is the phase difference between them. And the phase difference between these two is 60 degree. Sin 60 is root 3 by 2. So what you get is this. I RMS is 5 root 3 by 2. Okay? Chal betu. Last, fourth. Power dissipated at resonance in LCR circuit. At resonance, XC minus XL is 0. Phase difference is 0. So cos phi is 1. Power dissipated is nothing but I square R. Because at resonance, the value of impedance is R. So in resonance, the power dissipated is I square R. But to do realize this I is I RMS, not the maximum. Chalo, moving on. Last thing, transformer. There are two types of transformers: step up transformer, step down transformer. A transformer can be used to step up an AC or step down an AC. Now, listen. In a transformer, we have a primary coil and a secondary coil. And we put soft iron core between this primary and secondary coil. The job of this soft iron core is to do flux linkage. The number of magnetic field line which will pass through the primary, the same number of magnetic field line will pass through the secondary. Let's say the number of turn in primary is NP, number of turn in secondary is NS, and the flux linked with one turn is phi here and phi there. So you will say the total flux linked with primary equals to number of turn in primary into flux linked with one turn. Similarly, flux linked with secondary equals to number of turn in secondary multiplied by flux linked with one turn. Now do realize the more the number of turn you have on each side, on whichever side, the more will be the flux linked with it. The more will be the flux linked on changing the current, more will be the rate of change of flux, and more is the rate of change of flux, more will be the EMF. So the side which has more number of turn, in that side more EMF is generated. So just remember, EMF of secondary upon EMF of primary equals to number of turn in secondary upon number of turn in primary. It means that if the secondary coil has 20 times more number of turn, then the EMF generated in the secondary coil will be 20 times more. If the secondary coil has half the number of turn compared to primary, then in secondary, the EMF generated will be half. EMF is directly proportional to number of turn because the flux link with the coil is directly proportional to number of turn. So here we have got this. Potential in secondary upon potential in primary equals to number of turn in secondary upon number of turn in primary. Now, power equals to IV. If no power loss happens, ideal transformer. If no power loss happens, then current in primary into potential in primary equals to current in secondary times potential in secondary. Hence, potential in secondary upon potential in primary equals to number of turn in primary upon number of turn in secondary, which equals to number of turn in secondary upon number of turn in primary. So just think of it this way. If the secondary coil has, let's say, 10 times more turn, output secondary. If the secondary coil has 10 times more turns, it has 10 times more flux, it has 10 times more EMF, but the power is same. So EMF is 10 times, but power is same. So current has to be 1 by 10 times. So this same thing is written here. Okay. Current in primary upon current in secondary equals to potential in secondary upon potential of primary equals to number of turn in secondary upon number of turn in primary. Now better here, we have got last 3-4 points. We will do it. After that, tata bye bye. First, there are some losses in a transformer. First is flux leakage. To do the flux linkage between the primary and secondary, we put soft iron core. But some of the magnetic field lines escape this soft iron core. That's called flux leakage. There is always some flux leakage. That is, not all the flux due to primary passes through the secondary. Not every single magnetic field line which goes through the primary also goes through the secondary. Now, second point, resistance of the winding. The primary and secondary winding, they are made up of metal. Let's say copper. Copper is a good conductor, but still it has some resistance. So as the current will flow, there will be some heat dissipation. So the wire used in the winding have some resistance, and so energy is lost due to heat produced in the wire. Next, eddy currents. This soft iron core, when the current flows in the primary and secondary, within the soft iron core, eddy currents are formed. So the alternating magnetic flux induces eddy current in the iron core and causes heating. This is another way of loss. And last one is hysteresis. Hysteresis loss happens when you suddenly keep on changing the direction of magnetic field through a ferromagnetic material. The domains keep on aligning, disaligning in one direction, then another. This leads to a loss which is called hysteresis loss. So that's all. See you guys. All the best for your NEET examination. Tada, bye bye.